Welcome everyone to this section of the course covering the Pandas data analysis library for Python. Personally, this is one of my absolute favorite libraries in Python, and once you become very skilled with Pandas, which you will be at the end of this section, then you're going to have a huge level up in your skills, especially when it comes to analyzing data and organizing data. Pandas is an open source library for data analysis for Python. And it uses an extremely powerful table object called a DataFrame system, which is built directly off of NumPy. So it's extremely computationally efficient. All right, so what are the things we can actually do with Pandas, and why would we want to use Pandas instead of just opening up something like an Excel spreadsheet or a Google spreadsheet? Well, Pandas comes built in with tools for reading and writing data between a wide variety of formats. Not only can it read things like CSV files or Excel files, but it can actually connect directly to a larger SQL database and read and write data to that SQL database. And what's awesome about Pandas is it can intelligently grab data based on things like indexing, logic, conditional subsetting, and more, which we're going to cover later on in this section. It's also able to easily handle missing data and adjust and restructure data. Often people refer to Pandas as kind of Excel for Python, but it's really so much more than that. Basically, there's going to be larger files when you're working with data science and machine learning that you're not going to be able to open in a spreadsheet due to the limitations of that software. However, Pandas, when it comes to actually working with it, it's really only limited by how much RAM your computer has. And RAM, as we know, is getting cheaper and cheaper. So you're going to be able to open up really large files of Pandas and quickly perform analysis on them since it's all happening in memory in your RAM. Okay, let's get started. Welcome everyone to this lecture on the Pandas series object. A series is a data structure in Pandas that holds an array of information or data along the named index. The named index is really the aspect of a Pandas series that differentiates this from a simple NumPy array that we learned about in the previous section. As a formal definition of what a Pandas series is, it's a one-dimensional ND array with axes labels. So let's actually show you realistically what that means. So we already know that a NumPy array has a numeric index, which means if I have a NumPy array storing, for example, the years of independence of countries in the data, then I have a numeric index that's associated with that. So if I wanted to grab, for example, the year 1776, then I say, go ahead and index item 0 off this NumPy array. Now, that's all well and good, but the problem is that it'd actually be a lot more useful as far as the data is concerned, to have it associated with a string label. Because right now I have to actually memorize the positions of the years instead of memorizing or knowing the association I want with them. And so what a Pandas series allows us to do is supplement that index with a labeled index. So the Pandas series essentially adds on a labeled index that can be strings or names or really anything you want here. And you'll notice now I'll be able to grab information off this Pandas series based off the labeled index, which makes it a lot easier to grab data in an informative way. So I can say, go ahead and grab the series at index USA, and it would return back 1776. That's a lot easier to use than having to memorize those index positions. And it's more in line with what real-world data looks like. Something I want to clarify, however, is that the data is still numerically organized. And essentially, you can think of a Pandas series as just holding a NumPy array internally and then adding on that named index. So I can actually grab information through a numeric index call or this labeled index call within a Pandas series. So essentially now I get the best of both worlds. And it's still very computationally efficient to store data in this format. So you'll have both access to a numeric index and, more importantly, this supplemented labeled index. So what we're going to do is we're going to explore the various ways to create this Pandas series object. And we'll also learn about some key properties and operations. So let's head over to the Jupyter Notebook and explore a Pandas series. Okay, here I am at a new Jupyter Notebook. First thing I want to do is import NumPy as NP in case I want to create some data. And I'm also going to import Pandas as PD. And import Pandas as PD is the main convention used for importing Pandas objects. And what we're going to be working with is the Pandas series object. And you can check out the documentation online for more information about a Pandas series. Or what's really useful is if you just call help on PD, pd.series, note it's a capital S there, and hit Shift Enter, it's actually going to display the documentation here for you. And you'll notice it's very comprehensive. So it shows you all the methods available on a series. And if you keep scrolling down, it'll eventually actually show you examples. So here we can see examples of creating a series, how it deals with missing data, and so on. So there's a ton of information here. Granted, if you're this far down in this help function, I would just say go to the online documentation instead. It's going to be a little easier to read there. But it's always available for you here within an IDE by just calling Python's help on the Pandas series object. Let me go ahead and comment this out and continue. So if we say pd.series after importing Pandas' PD and do Shift Enter here, we have the documentation string or the signature here for the main ideas of what we need to pass in to a Pandas series. Lots of things like data, index, data type, name, and so on. But the main things we have to be concerned with here is data and then index. And that's really what's going to add on the supplemental index to the data, which is stored as a NumPy array within the series. So in fact, let's create real quick 2 objects. We'll create them as Python lists, just normal Python lists. We're going to create an index, USA, Canada, and let's say Mexico. So it's in line with what we're showing in the slides. And then we'll say my data is equal to, let's say their years of independence, 1776, 1867, and then 1821. And so what I'm going to do is create a series object by saying my SER, my series, is equal to pd.series. And we're going to say the data is equal to data, or my data actually. So we're passing in right now just data as a normal Python list. And if we run this and essentially ask for what does my series look like, you'll notice that Pandas immediately reports back your data organized internally. And internally, it's essentially converting this Python list to a NumPy array held inside as a Pandas series. So if you check the type of this object, it's going to report back that it's a Pandas series now. So it says pandas.core series. And you'll notice that automatically it's going to show you the default numeric index. But as we just explored within Pandas series, it also takes in this index parameter. So now let's not just provide data, but let's also provide index. So we'll say index is equal to, and now I'm going to pass in these string codes here because it's going to be a lot easier to look up information based off the string that I know, such as USA, instead of having to memorize, position 0 for 1776. So I'll say index is equal to my index. Run that again to redefine the series object. And now we can see that the index is this labeled string index, which means I can actually grab information off of this almost as if it was a dictionary. So we'll say my series, and then I can say at 0, and it'll return 1776, or I can say my series at USA, and it also returns 1776. So you'll notice that the series object now retains both this numeric index by location and this labeled index, which is what we're going to be using throughout the course. Typically, we're going to have a labeled index, which is going to be easier to read than just searching for strings numerically. One more thing I want to point out is I'm being explicit here as far as what the arguments represent, such as data equals and index equal. Obviously, as long as I provide them in the correct order, that's not necessary. I can just say my data comes first, then my index comes second, and if I rerun these, it's the same thing. So typically, you're not going to be so explicit as far as the arguments are concerned, as long as you pass them in the correct order. I'm just doing it so it's very clear what the data is and what the index is. Okay, so that's one way of creating a series, essentially defining an index or defining data. And we saw that at a minimum, all we need to define is the data. And Pandas will, on its own, create that default index of 0, 1, 2, all the way to however many entries you have. We can also create a series from a dictionary. So let's go ahead and create a dictionary. We'll say ages is equal to, and what I'm going to do here is just create a couple names, such as Sam. Let's say Sam is 5 years old. We'll say Frank. Say Frank is 10 years old. And we'll say these are the ages of dogs or something. We'll say Spike is 7 years old. And what's interesting here is what I can do is if I have a dictionary like this, I could easily pass it into Pandas series and say, this is just my data. And Pandas is smart enough to make these dictionary keys the index and make the values the array data. So if I run pandas.series, what it's going to do is it's going to automatically transform this into a series. And that's really useful because as we learn about more libraries within Python, a lot of times they return the information in the form of a dictionary. So it really helps to easily organize that information, just passing it into a Pandas series object. All right, so we'll conclude this lecture on the very basics of series, and in the next lecture, we'll continue on by showing you various operations you can perform with a Pandas series object. The main thing you should have gotten out of this lecture is that a Pandas series will go ahead and take in data, and if you want, it'll go ahead and take in a labeled index. And if you pass in a dictionary, it will automatically transform that into a labeled index with corresponding values. As a quick note, the notebook that we're referring to is the first notebook here and under the Pandas folder. It's called 00-series. And if you open up that notebook, you can go ahead and scroll down to where we begin discussing the key ideas of a series, such as a named index. And what I'm going to do is I'm going to copy the input for cell number 32 in that notebook, which is essentially just 2 dictionaries. And these dictionaries are essentially imaginary sales data for the first quarter of a company and the second quarter of a company. So it's just to easily create 2 series objects from a dictionary. Save ourselves a little bit of typing by just copying and pasting this from the lecture notebook. And then what we're going to do here is we're going to convert this into a Pandas series. As we discussed earlier, I can just create a variable name and then say PD series, and we'll pass in this dictionary Q1. And let's say sales Q2 is equal to PD.series Q2. Again, remember it's capital S there. And so what I have here for sales Q1 is this Pandas series where I have a labeled index of a country, Japan, China, India, USA, and then let's say the sales values for those particular countries in, let's say, quarter 1. And if we check out quarter 2, sales Q2, then I have sales for the second quarter of this imaginary company, Brazil, China, India, USA. So again, a couple of things to notice here is I can, as before, grab items based off the label index. So I can say, okay, sales Q1, what's going on, let's say for the country of Japan. I run this and it tells me my sales for Q1 were $80. Or I can also do this based off a numeric location. So if I somehow knew I wanted the very first item in that series, I would say 0 and returns back 80. Obviously, it's a lot more clear if we start using that labeled index what 80 actually represents here. So I would encourage you to set up your data in a way where if you're doing some sort of grabbing of data, you try to use a named index. So it's clear when you review your code or send your code to someone else, they can easily read it. This is a lot more readable than just passing in 0. And something to keep in mind, a super common mistake is accidentally passing in the wrong key here. So the key has to be exactly what the key is inside the actual series. So if you were to lowercase this to Japan, it's going to say there's a key error because it's key sensitive or it's case sensitive. So you'll notice here lowercase j doesn't work, or even if you do something, which is a really common error of accidentally having, for example, an extra space. So if we say Japan, accidentally put an extra space there, it'll say key error Japan. So just keep that in mind. If you actually want to see what keys are available to you inside a series, because maybe you're having trouble actually finding it, you can say sales Q1 or whatever the name of your series is and say keys, open and close parentheses, and then it's actually going to return back this index object, which is your index objects in order. So we can see that here. Okay. So this was one really easy way of finding out, oh, what's the exact string for whatever I'm looking for? Okay. So we know how to grab the keys and we know how to grab stuff based off the keys. Let's go ahead and discuss the very basics of operations between 2 series. So what's really nice about Pandas series objects is because they're built off a NumPy array, then we can actually perform broadcasted operations on them. So recall if I have a list such as 1, 2, and if I were to try to multiply everything in that list by 2, we already know something like this doesn't work. because what it's going to do is essentially going to double up that list, when really what I want to do is multiply each item in that list by 2. However, we do know that if it's a NumPy array, this operation gets broadcasted, and then it gives us the results we expected, 2 and 4. And luckily, since a Panda series is built off a NumPy array, then the same happens here. If I say sales Q1, it's going to report it back by the broadcasted operation, which means we can do stuff like start easily getting things. Maybe we want to divide by 100 or something like that to get it into some sort of percentage format. And we can easily do that within a Panda series itself. So you can broadcast these sort of operations. And what's nice is because we have a labeled index, when we perform operations between two series, it's actually going to take the labeled index into account. So what do I actually mean by that? You see that I have sales Q1, Japan, China, India, and USA. And if we take a look at this company's second quarter sales, you'll notice it says Brazil, China, India, USA. So what's actually happening here is we have information on Japan in Q1, but not in Q2. Instead, it got replaced by Brazil. So what happens if I'm trying to calculate my total sales for the first half of the year? Essentially, I want to say sales Q1 plus sales Q2. Well, if I say sales Q1 plus sales Q2, and I run this, by default, Pandas is going to be smart enough and match things up based off their labeled index. However, it's technically not smart enough to know what it should do in the case of the labeled indices not being present in both series or the multiple series you're adding up together. So instead of replacing it with a value, it will actually show you not a number and not a number for Japan. And this is actually a good way of Pandas essentially telling you, hey, Brazil and Japan are not present in both these series. Now let's say you, as the user, actually know that to be the case, and you want to fill in some value by default when it's not present in the series. Essentially, for example, you want Brazil in Q2 to be 100, and in theory, you want Brazil in Q1 to be 0. That way, this actually shows up as 100 when you add them together, and Japan shows up as 80 when you add them together. So while this is nice, that Pandas warns you, hey, Brazil and Japan aren't present in both these series, let's say after adjusting our evaluation, we say, that's okay, I need them to be filled in of some value. Well, to do that, we say sales Q1, and then what we're going to do is we call the add method on it. So we no longer use Python's base operators. Instead, we're going to have to call add. And if you do tab here, there's going to be a list of operations. So for example, if you wanted to do some sort of multiplication, it's going to be MUL or multiply. So keep that in mind. If you wanted to do division in this sort of format, it's going to be div or divide. You'll notice there's kind of two names here which do the same thing. So one's a little shorter than the other, but we want to add them. So I want to say sales Q1 added to the series sales Q2. So in parentheses with this method call, it says, hey, what's the other thing you want to add in here? And then it also takes in a fill value. So we'll say sales Q2, go ahead and add it. And then if we see what does that actual fill value represent, I scroll down here and it says the fill value is what you should fill in for existing missing values. So essentially, what are you going to fill in for Brazil and Japan if they're not present in both series? And in this case, a reasonable fill value is 0, since we made 0 sales for whatever quarter they're not present in. And now I can say fill value is 0. I run this and I get back the results I want. I see Brazil is now 100 and Japan is 80. The last thing I want to point out here before we finish off this lecture is you'll notice that my original values were in integers. In general, as soon as you start doing numeric computations with any objects within Pandas, it's going to quickly convert them into floating point numbers. So it's just something to keep in mind. You can always specify the data type or change the data type of a Pandas series as you go along. In fact, it's one of its attributes you can access by saying dtype. And the original one you can see is integer 64. But if I say first half is equal to sales Q1 added to sales Q2, and then check the integer type, or excuse me, the data type there. So first half D type. You'll notice now it's a floating point number. It's just something to keep in mind. Typically for our operations, we're not going to be concerned with things being transformed from an integer to a float because the math is still going to work out to our favor. It doesn't matter if we have 1 or 1.0. So throughout the course, we're not going to worry about this. But if you have a situation where you need them to be integers, you can always either round them off using np.round or pandas round, or you can just specify or hard code the data type in your operations to be whatever you're looking for, 64-bit integer or 64-bit float, and so on. And in fact, if you look back up to pd.series, or if we just call it here, pd.series, there's data index, and there's also data type. So you can actually specify the data type for this series. And if you want, you can also name the series, which is just going to be a name that's kind of this high-level label for this series overall. All right. So that's the very basics of a Pandas series. Main thing to note here is that when you perform operations with two series, Pandas is going to be smart enough to understand that they're labeled and that they should perform the operation on the labels. However, if you have a special case where you don't want null values and instead you want them filled in with something, you'll have to call these special method calls. Okay. Welcome back, everyone, to this lecture series on data frames. So throughout the course, most of our data exploration is actually done with data frames. And data frames are an extremely powerful tool and really just a natural extension of the Pandas series. And a data frame is a table of columns and rows in Pandas that we can easily restructure and filter. And as a formal definition, a data frame is simply a group of Pandas series objects that share the same index. And that's actually a really important definition and distinction to make. So let's quickly define this a little visually. So here we have an example of just a single series, something we're already used to from the previous lecture, where we have a labeled index, and then we have some data columns, such as the year. Now here we have an example of multiple series that are actually sharing the same index. You'll notice that each of these individual 3 series actually has the same index, USA, Canada, Mexico, and so on. And so what we can do is combine these 3 series that share the same index into a single data frame with the same index, just with the multiple columns. And so that's all a data frame is. It's just several series that happen to share the same index. So this looks a lot like a spreadsheet, which is essentially what it is at a very high level overview, where each individual column is just a Pandas series, and they all just share the same index. Okay, let's get started showing you how to create a data frame from Python objects. I'm going to head over to a Jupyter Notebook. All right, here I am at the Jupyter Notebook. I'm going to go ahead and say import numpy as np and import pandas as pd. And I'm going to do one last thing here. I'm going to say from numpy.random import rand n. And then I'm going to go ahead and set a seed. And what a seed means is just to make sure that we get the same random numbers. That way, if you're following me, you'll see the same random numbers that I see. So you can go ahead and say np.random.seed. All right, let's go ahead and explore the DataFrame command. I'm going to say df is equal to pd.dataframe, and you can actually use tab here if you're using Jupyter Notebook to autocomplete this. And notice that the F is capitalized. I'm going to do Shift tab to check out the docstring and the initial signature for this PD data frame. We have a data argument and an index argument, just like we did for series, but then we have this additional columns argument. Let's go ahead and build this up with some random data, and we'll see what a data frame actually looks like. First thing I'm going to do is pass in that data argument, and I'm actually just going to call it rand n 5, 4. And then the next ones we want to pass is the index. And the index, we can just make that a list of characters here. I'm going to go ahead and say A, B, C, D, E. And then finally, for the columns, I'm going to go ahead and say W, X, Y, Z. So I'll say W, X, Y, Z. I'm going to go ahead and run this and then pass in the data frame, just display it. And there we get a nice display, and this probably looks and feels a lot like Excel if you're using a Jupyter Notebook, and that's good. If you're using another IDE editor, you may not get such a nice crisp display, but you should get a printed output that looks similar to this. Alright, so basically what we have here is a list of columns W, X, Y, Z and corresponding rows A, B, C, D, E. Now, each of these columns is actually just a Pandas series. So W is a Pandas series as well as X, Y, and Z. And they all share a common index. And that's basically all DataFrame is. It's just a bunch of series that share an index. Let's go ahead and show how we can use indexing and selection to actually grab one of these series objects or several of these columns out. One way, and the main way to do this, is by saying df and then using bracket notation and then passing in the column name. In this case, let's go ahead and grab the W column. So as a string, I'll pass in W, and this returns the W column. And now take a look at the output. Now this actually looks like a series. And that's because that's exactly what W column is. It's just a series. And you can actually confirm this by saying type of df of W. And it shows that it's pandas.core.series.series. If I just say type on the df object itself, I will get a data frame out. So again, just to reiterate that fact that a data frame is just a bunch of series that share the same index. Now, there's two different ways you can grab a column from a data frame. The main way, and the way you should always do it, is using this sort of bracket notation and then passing the column name. However, if you're really familiar with SQL, a lot of times you're selecting a column, you pass in a table, dot, and then the column name. This actually also works for Pandas. You could say dot and then the column name. However, I would recommend that you don't use this because it may get confused with the various methods that are available off of a data frame. For instance, if I say df dot and then click tab, I see a whole bunch of methods available for me. And those are a bunch of methods that we're going to learn about as we learn more about Pandas. But what may happen is that one of these methods gets overwritten by a column name. And then Pandas is going to get confused whether you're asking for a method or an actual column name. So what you should do to avoid that is always use this sort of bracket notation when requesting a column. Okay, if you want multiple columns back, then you can go ahead and pass in a list of columns. So note that I pass in my brackets and then I'm going to pass in a list of column names, which is going to result in another set of brackets here. For instance, if I wanted columns W and Z, I pass in a list here highlighted, W and Z, and I get back a data frame containing those two series. And that means when I ask for multiple columns, I'm actually getting back a data frame. If I ask for just a single column, then I will get back a series. And in the Jupyter Notebook system, that's denoted by the way the output is displayed. Okay, let's go ahead and move on to creating a new column. Pandas supports creation of new columns by just specifying the column as if it already exists. For instance, new. Now if I run this, I'll get an error, and it's a key error. If you scroll all the way down here, it'll say key error, new, and it basically just is trying to tell you that it can't find it, that there is no key new there. However, when you're creating let me go ahead and hashtag that out and put this back in. When you're creating a new column, you can actually define it as if it already exists, and then on the right-hand side of this equal sign, use other columns with arithmetic in order to pull off a new column. For instance, we can say df new column as if it already exists is equal to dfw plus dfy, and this will run with no error. And now if I check out df, that new column is actually in place there. And for removing columns, you can say df.drop. You can say df.drop and pass in the actual column name you want to drop. Now, if you just do this by itself, you'll get an error. And let's go ahead and check out what that error is. It'll say value error, and we scroll down, it says labels new not contained in access. And if I click Shift Tab on the drop method, notice that by default it says access is equal to 0. Access is equal to 0 for the drop method refers to the index. If I actually want to refer to the columns, I need to specify access is equal to 1. And then it will drop that new column here. Now there's two things to note when using this df.drop. The first thing to note is that this doesn't happen in place, meaning I'm not actually affecting this data frame unless I specifically specify this to occur in place. I'm going to go ahead and show you what I mean by that. I've called this line df.dropNew axis equal to 1. If I call it df, I'll see that I still have that new column. That means I need to actually specify as an argument, I will do Shift Tab to show it, the in-place argument. And many Pandas methods will require this in-place argument to be set to true. And the reason Pandas does that is that for you not to accidentally lose information. In case you've done a bunch of adjustments to your data, you don't want to accidentally lose it. So Pandas requires you to say in place equals true if you actually want a lot of these changes to stay and occur in place. And now if I call df by running this cell, notice that new column is now permanently removed because it occurred in place. And something to note here is that we can also use df.drop to drop rows. For instance, let's go ahead and use this to drop the E row. I'll say df.drop. I pass in E, and I can also say axis is equal to 0. Now remember, you actually don't have to add that in as an argument. That's the default. So let's go ahead and just say df.drop E. And there we've been able to drop the E since axis is equal to 0. And it works either way. I could say axis is equal to 0, and this will work again. And note here, I'm not doing this in place. Okay, sometimes a point of confusion is why are the rows 0 as far as their access, and why are the columns 1? Well, a reference actually comes back to NumPy, since data frames are essentially just fancy index markers on top of a NumPy array. To show this, I can say df.shape, just like we did with a NumPy matrix. And note, df.shape is a tuple for a two-dimensional matrix here, and at the 0 index are the number of rows. So if I say df here, I have 5 rows, A, B, C, and D, E. And then on the index 1, I have 4 columns, W, X, Y, Z, which is why rows are referred to as the 0 axis and columns are referred to as the 1 axis, because it's directly taken from the shape, just as you would with a NumPy array. Okay, now let's talk about selecting rows. We've talked about selecting columns, which you just do by saying df, and in brackets, you pass in the column name. Or, if you want many columns, you pass in a list of the column names, such as Z and then comma X. Let me close off that bracket. So I'm passing a list of column names, and I return a data frame of those multiple columns. Let's talk about selecting rows. I'm going to take a look at my data frame again. Here's my data frame. A, B, C, D, E is my rows. W, X, Y, Z are the columns. There's 2 ways to select rows in a data frame. And you have to call a method off of this. And there's 2 methods to use. One is loc, L-O-C for location. And this is going to take in a label. So you can also do Shift Tab here to see this property. And something to note here is I'm using square brackets, which is a little weird, but that's the way it works with Pandas. You pass in .loc, and then you pass in brackets the row you want. For instance, if I wanted the A row, I just pass in .loc, I pass in the label of that index. And this returns, note, a series. And this comes to our second conclusion that not only are all the columns series, but the rows are series as well, as far as the way they're going to get returned when you request them in Pandas. Now let's discuss the second way to grab a row, which is based off of index position. I can use df.iloc to actually pass in a numerical index position even if my axes are labeled by strings. For instance, if I want C, that row, I can do that 2 ways. I could either say df.loc for location, and in brackets pass in the row name, which is C, or I can say iloc, which is index-based location, and count what index it's at, so 0, 1, 2. And then on iloc, pass in 2, and this also returns that row. And that basically means you have 2 ways of selecting rows, using LOC if you want the location or labeled-based index, or iloc if you want the numerical-based index. Okay, let's talk about selecting subsets of rows and columns. And this will actually be very familiar to you since we just learned about NumPy. We can say df.loc. If we want to select a subset of rows and columns, we can pass in, just like we did with NumPy, using comma notation, the row we want and then the column we want. So I want the value at row B, column Y. And this returns just a single value there. So if I take a look at my df again, looking at row B, column Y, I have this negative 0.84, and I get the same result here. So just like NumPy, you can use this row, comma, column notation. And if you want a subset of this, you can say df.loc and then pass in a list separated by commas. For instance, let's say I wanted the subset of AB rows with the WY columns. So basically I wanted this 2.7, 0.9, and 0.65, and negative 0.84. That means I can just pass in a list of the rows I want, which in this case is A and B. And then I can pass in a list of the columns I want. In this case, that's W and Y. Shift enter that, and I get the subset return of the data frame. Okay, we're going to stop it here for now and continue this discussion in part 2 of the DataFrames lecture. And this is all in the notebook called DataFrames under the Pandas folder. Let's get a quick review of what we've learned. As far as creating a data frame, you just need to say pd.dataframe, pass in your data, pass in your index, and then pass in your column names. Usually we won't be building data frames by hand in this manner. We'll actually be reading data from some sort of source, like a CSV file, but we'll learn how to do data input and output later. For now, if you want to manually create a data frame, that's how you can do it. Then, for selecting columns from a data frame, you can say df, and then in brackets, pass in the column you want, or pass in a list of the columns you want. Remember that each column is actually just a series. You can create new columns based off of old columns by using this sort of arithmetic. Then you can drop columns or rows using df.drop. Remember, you'll need to say in place equals true if you want the effect to be permanent. You say axis 1 for columns, and then axis 0 for rows. And again, that comes from this shape tuple. 0 index was rows, 1 index was columns. As far as selecting rows from a data frame, there's 2 methods here. There's the .loc method, which is a labeled-based index location, or there's the .iloc, which is the integer-based index location. And then if you want to select subsets of the data frame, you can use .loc and pass in either values or complete lists to return subsets of the data frame. Okay, that's it for the very basics of data frames. Coming up next, we're going to discuss even more of what you can do with a Pandas data frame, such as using conditional selection. Last time we left off on how to create a basic data frame and grab information from that data frame. Now we're going to look at conditional selection as well as some multi-index parts of a data frame. Let's go ahead and jump to Jupyter Notebook to get started. Alright, here we are back at the Jupyter Notebook. I'm going to be using the same data frame as last time. So remember we just had to say numpy is np, pandas is pd, import rand n, set the c to 101, and then say the data frame was rand n 5, 4. And then here we have our data frame. Okay, let's go ahead and talk about conditional selection. A very important feature of Pandas is the ability to perform conditional selection using bracket notation. And this is going to be very similar to NumPy. For instance, if I use a comparison operator against a data frame, such as asking where is the data frame greater than 0, I will get a data frame back of Boolean values, where it returns true if the data frame value at that point was greater than 0, and false if it was not greater than 0. And this is very similar to the same conditional selection applied to an entire NumPy array, except in this case, we're doing it with Pandas data frames. And just like this, we can go ahead and say bool df is equal to df greater than 0. And then say bool df, go ahead and check that out. And here we have our Boolean data frame. And if we pass that in to our original data frame with bracket notation, then we will get out as a result values where it was true and nulls or NaN where it happened to be false. And that's the way you can use conditional selection along with a data frame. Now, usually you probably wouldn't be separating this out into two steps. You would just say df and then in brackets, something like df greater than 0. And you would get this result. This sort of operation with a data frame and against a comparison operator isn't that common. What most likely you'll end up doing is instead of just passing in the entire data frame, you'll pass in a row or a column value. And instead of returning nulls, what that's going to do is return only the rows or columns of the subset of the data frame where your conditions are true. And let me go ahead and show you an example of what I mean by that. Let's go ahead and take a look at our original data frame. Here we have rows A through E and columns W through Z. What I'm going to go ahead and do is specify df of W greater than 0. And notice I get a series back. True, true, false, true, true. And this is linked to the actual index. And if I take a look at the W column, I see that this corresponds with the W column values. And the value at index C was actually less than 0, so it returns false for being greater than 0. I can now use this series of Boolean values corresponding to rows to filter out rows based off of a column's value. And that means if I pass in this series into a data frame using bracket notation to say something like df of dfw greater than 0, I will only get back the rows where this happens to be true, meaning I'll only get back the rows A, B, D, and E. It won't return row C since it was false here. Let's go ahead and run that and see what this looks like. Great. And now, since I'm passing in a series, I don't get those null values anymore. You only get those null values when you're doing this sort of condition on an entire data frame. When you're actually passing in conditions based off of columns, you'll just get series values, meaning you'll get only the rows where it happens to be true. And this is the sort of conditional selection we're going to be using most often throughout this course. Let's go ahead and show just a few more examples to really drive this point home. Let's say I want to grab all the rows in my data frame where Z is less than 0. So I say df, where df of column Z is less than 0. Now let's take a look before we actually run this, what should happen. Well, we'll notice column Z, where is it less than 0? Well, that's only occurring in row C. So column Z as in Zelda, and then row C as in cat. Here, this is the only row that should be returned. But remember, we're asking for the entire data frame back, so it should return just this row C for us. And there it is. Okay, great. Now, something else to note here is that when you're doing these sort of commands, let's go ahead and go back to our W greater than 0, you get a data frame in response. And that means you can go ahead and call commands off of this data frame. And you can do this either in one step or two steps. I'm going to go ahead and say result df is equal to this, and then take a look at result df, which is the subset of the data frame without that row C in it. And that means I can go ahead and grab results off of this, such as x. And here I have 4 values of x, A, B, D, and E, based off of this resulting data frame that didn't have that row C in it, as in Charlie. But instead of actually separating this out into two steps, such as grabbing the x column, I can do this all in one step. And let me show you what I mean by that. I can go ahead and say, return the data frame where the column value of W happens to be greater than 0. So return those rows to me. And that means all the rows minus the C row. And since this is the data frame, I can actually go ahead and stack commands such as bracket notation on top of it, such as return the X column where that's true. And now I get the same results as I did up here, except it's all done in one step. And this is something that can be intimidating to beginners at first, since there's a lot of brackets and a lot of stuff going on here. But essentially, this is just, instead of splitting everything up into multiple steps, I'm putting it all into one step. And likewise, since this is a data frame, I can bracket for multiple columns by passing in a list, such as y, x. And we can see we get a result here. Let me go ahead and break this line down one more time to show the steps that we're taking. First off, we're going to go ahead and say bool df is equal to, well, let's go ahead and say bool series, since it's a little more accurate. is where DFW is greater than 0. So if I say bool series, I get this Boolean series back. Then what I'm going to go ahead and do is say result is equal to DF of that bool series. Let's go ahead and check out the result. And it should just be wherever that series was true, which is A, B, D, and E. And there is my result. That's the entire data frame without the rows C in it. And then I can go ahead and off of that result, call a list of columns. So we can go ahead and say Y, comma, X. And if we wanted to, we could actually even separate this out into one more step by saying my calls for columns, pass in that list, and then say result of my calls. And we get the exact same thing we have here done in one line as in multiple lines. That means if you're ever confused on something that looks like this with a ton of brackets and pandas, see if you can break it down into multiple steps if that makes more sense to you. Throughout the course, we're going to be doing this type of notation, these kind of one-liners. And as you get more and more comfortable with pandas, you'll find yourself using these one-liners more and more often. But if you're ever confused, always feel free to break it down into multiple steps. The only disadvantage as far as breaking it down to multiple steps is that you are taking up memory with each variable that you define. So as you get better and better with pandas, you'll want to move towards this simple one-line abstraction of all these commands. All right. Go ahead and pause the video now and really make sure you understand how line in 58 here is the exact same thing as separating it out into multiple lines. All right, let's go ahead and explore real quick the concept of using multiple conditions, such as 2 or more conditions. Right now, we feel comfortable with doing something like this, which is returning a subset of the data frame based off of one condition. But what if you wanted multiple conditions, such as where W was greater than 0 and Y was greater than 1? Well, what you could do is try something like this. Is in parentheses, pass in one condition, and then say and, pass in another condition. And this is going to return an error. And I'm going to do this on purpose to explain why there's an error happening here. And this is a common mistake for beginners to put this and here. And you'll get a mistake that says something about the series being ambiguous. If we scroll down here, we see this. The truth value of a series is ambiguous. And what that is trying to say is that Python's normal AND operator can't actually take into account a series of Boolean values compared to another series of Boolean values. An AND operator can only take into account single Booleans at a time. So true and false returns false, true and true returns true, etc. That means when you pass in an entire series of Boolean values, such as this, the AND operator begins to get confused. It can only deal with these single instances of Boolean values, which is why when you're working with pandas and you want multiple conditions, you actually have to use an ampersand, which is this AND. So that's going to be Shift 7 on your keyboard for most standard keyboards. And notice here that I'm passing these conditions in parentheses to show clear separation between each of these conditions. And then if I run this, I get the row E where this happens to be true. Okay, let's go ahead and break that down one quick last time. When you're trying to use multiple conditions, you can't use Python's normal AND operator. You have to use the ampersand. And then you pass in the multiple conditions in parentheses, and then finally you put it inside of brackets for your data frame. If you want to do an OR operation, you can just replace this with the pipe operator, which is right above your, usually for most keyboards, on your enter key, go ahead and go right above it and then do shift on that, backslash, and this should give you the pipe operator. And that's going to be your replacement for OR, because if you try using OR, you'll get the same error. So that's with OR. If I try it with Python's normal OR, again, I'll get the truth value of a series is ambiguous. And that's because you get a series of those values instead of just 1 or 2 Boolean values. Okay, you can go ahead and reference in notes if you want more examples of this. But basically, if you want multiple conditions, pass in each condition in parentheses and then use an ampersand or pipe operator for the AND or OR. Let's go ahead now and shift gears to talk about index and a little more details about it. what we're going to discuss now is resetting the index or setting it to something else. Let me go ahead and take a look at our original data frame. I'm going to go ahead and clear these cells here by just running them. And let's take a look at our data frame. Again, we have rows A through E and columns W through Z. In order to reset the index back to the default, which is just a range index 0, 1, 2, 3, 4, all the way up to the nth row, what you can do is call the method reset underscore index. And remember to close parentheses that we actually run that method. And if you call that, notice you will get the index reset to a column. And you'll get the actual index then to be numerical. And that's how you can reset the index. Something to note here is just like a lot of other Pandas data frame operations, this doesn't occur in place unless you specify it for it to occur in place. So if I call back df, I still have that original index of labels. If you want this to actually occur in place, what you would just do is say in place equals true and pass it into the reset underscore index. For now, we'll go ahead and not do that. That way we still retain our original data frame. Let me go ahead and clear this out. Again, if you just want to reset the index to a numerical value, you can just use .resetIndex and your old index will become a column of your data frame. Okay, let's go ahead and show one more new index example, such as setting the index. And in order to do this, I'm going to go ahead and create a new index called new IND. And I'm going to use a little trick here that I'll explain in just a second. This is going to be a bunch of state abbreviations, and I'm going to say .split on this string. And remember, .split off a string is just a common method for splitting off of blank space. But this is a nice quick way to create a list instead of having to type out every comma. So I'm going to go ahead and set that list equal to new IND. So I have my new index values here. And what I'm going to do is put this as a column in my data frame. So I'm going to go ahead and say df states is equal to new IND. And since the dimensions match, so there's 5 items here, it will match from 0 to 4 here on this data frame. So if I check out my data frame, I have this new column called states. CANYWYORCO. Now we know how to reset the index, which is just doing the .reset underscore index method. But if you have a column in your data frame that you want to be the index, what you can go ahead and do is say .set index instead of reset index. For example, I can say df set underscore index and then pass in the column name you want to be the new index, such as states here. And if I do shift enter, now the states column has become the index. Keep in mind, unless you retain this information of the index, this will overwrite your old index and you won't actually be able to retain this information as a new column, unlike reset index that allowed you to have that new column. So that's set index versus reset index. Again, if I check out my data frame here, this wasn't in place. I would need to add the argument, if I do shift enter here, in place equals true. Let me go ahead and just do a quick review of what we just covered before we head up to part 3. Okay, we learned about conditional selection, which is very similar to NumPy operations. You basically get a data frame of Boolean values, and if you pass in a whole data frame of Boolean values, you'll get the values where it's true, and you'll get NaN or null values where it was false. If you pass in a series of Boolean values, such as a column with a comparison operator, you'll end up only getting the rows of the data frame where the series happened to be true. And you could break this down into multiple steps if you wanted to. Again, these 2 cells are probably the most important to understand out of this lecture. If you understand this, then you understand how to do conditional selection in Pandas. Then, scrolling down, if we wanted to do multiple conditional selection, you could do an ampersand or a pipe operator. You cannot use Python's built-in and or operators because of the ambiguous values in a truth series. And remember to use parentheses to separate each conditional selection statement. Then finally, we have reset index. Reset index is just going to reset your index to a numerical index and take your old index and set it as a new column called index. And then you can set a new index instead of resetting a new index based off a current column just by saying set_index. And both these methods are not in place by default, so make sure to specify in place equals true if you want the change to be permanent. In this final lecture of the DataFrames series of lectures, we're going to learn about multi-index and index hierarchy. We'll first create a quick example of what a multi-index data frame looks like, and then how you can work with data frames that have a multi-level index. Let's go ahead and jump to Jupyter Notebook to get started. Alright, here I am at the Jupyter Notebook. What I'm going to go ahead and do is copy and paste some lines of code that are available for you in your notebook called DataFrames. If you scroll down until you get to the multi-index and index hierarchy section, you'll see these 4 lines of code. These are the 4 lines of code we're going to use to actually build this data frame. We can go ahead and check this out. We'll say outside, and that's just a list. So we have 6 items in this list of 2 different types, G1, 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 and then G2, G2, G2. We have inside, which is 1, 2, 3, 1, 2, 3. And then what we went ahead and did was using the zip function along with the list function, is we said higher index. We went ahead and used zip and list on this in order to make this into a list of tuple pairs. So G11, G12, G13, G21, G22, G23. And then I passed it into a special function from Pandas. And we actually won't be working with this function at all throughout the course, but this is just for a customization of making a data frame. So don't worry too much about it, but I just want you to be aware of it. It's pd.multiindex from tuples, and it can basically take in a list that looks like this and create a multi-index from it. So after you're done with that, you'll get this multi-index with several levels. G1, G2 as one level, 1, 2, 3 as another level, and then labels. And we'll go ahead and explain what all that means as we create this data frame. But for now, you can just feel free to copy and paste this code directly from the notebook, since it's not important as far as creating the data frame from scratch. We'll go ahead and say pd.dataframe, pass in rand_n 6, 2. So we'll have 6 rows by 2 columns. And then I'm going to set the index to be the higher index object we just made. And then I will set the columns to be a list of A and B. Alright, and you can feel free to copy and paste all this code from the notebooks because it's not that important. This is just for actually constructing a multi-index level data frame. And let me show you what I mean by that. Here, if I actually show the data frame, I can see that it has 2 levels of an index. It has this G1 and G2 level, and then this sub or inside level 1, 2, 3, 1, 2, 3, and then 2 columns. And this is what a data frame looks like when it has multi-levels of an index, otherwise known as an index hierarchy. Let's go ahead and show how we can actually call data from a multi-level index. For this index hierarchy, what we can go ahead and do is say df.loc, and then we can go ahead and, using bracket notation, grab from the very outside index. For instance, if I want everything that's under G1, I can just pass in G1, and I get that little sub data frame in return, which is basically these first 3 rows for those 2 columns. And then I can continue indexing off of this, such as ILOC or .loc, either one's fine, and then passing in a number. And that will actually then return these 2 items here as a series. So the basic idea is you call from the outside index and continue calling inside deeper. If you actually want to name these index names, so right now they are unnamed, that's notified by the fact that there's no name in these 2 cells, which you can go ahead and do is say df index.names, do shift enter, and you should get a frozen list that's none, none. And this is just a pandas index names object types. All it's saying here is that these indices don't have any names, which you can go ahead and do is say equals, and then pass in a list of names. For instance, let's go ahead and call this outside index groups, because it starts with G, and then we'll call the inside index NUM for numbers. And now when I call my data frame, we have groups as a labeled index on the outside, and num as a label index on the inside. And this can have as many layers as you want. Hopefully you can begin to see how this would be useful for multi-level index information that you want to use along with a data frame. Let's go ahead and show you how we can grab information off of this one more time. Imagine we wanted to grab this value right here, 0.072, the one I have highlighted. Well, that's under G2, number 2, column B. Let's start from the outside and work our way in. We'll go ahead and specify that we want .loc G2. And that returns this data frame. Again, we're looking for this value here. So let's go ahead and do one more index. And we can go ahead and call here 2. And then we have under column B, or index B, excuse me, for the series 0.07. So then finally we just call B at the end. And that's how we can grab all the way from the outside to the inside this particular value. What you should do now is pause the video, select another value, and see if you can successfully index it and return it back. Okay, hopefully you're able to do that. Let's go ahead and show you one last very useful function called cross-section, and it's going to be XS. So this returns a cross-section of rows or columns from a series or data frame, and you're going to use this when you have a multi-level index. So again, our data frame looks like this. Let's say we wanted to grab everything that was under G1. I could do what I just showed you, LOC G1, and that returns the data frame under G1. But another option for a multi-level index is using this XS, this cross-section, and then passing in G1 also as a string. But what's nice about this cross-section is it has the ability to skip or go inside a multi-level index. For example, let's say I have this data frame here, and I want to grab all values of number equal to 1 with both groups in it, meaning I want what I highlighted here, 1 and then 0.3 and 1.69, but also I wanted this value, 0.16, 0.18. So I want all values where num, that inside index, is equal to 1. This sort of indexing is tricky for something like .loc methods, but it's not so bad with the XS or cross-section method. What you end up doing is specifying what you want as far as num equal to 1, and then you have to indicate as a second argument level and then pass in the name of the index. In this case, the name of that index is num. So essentially this allows us to grab a cross-section where level equals num is equal to 1. And that's how you're mainly going to be using this cross-section. And now we see both groups where level num happens to be equal to 1, and this sort of data frame gets returned. Okay, don't worry too much. This is pretty advanced usage of pandas. I just want you to be aware of it. Thanks everyone, and I'll see you at the next lecture. Welcome back everyone to this lecture series on missing data. In part 1, we're going to give you an overview of the options you have when dealing with missing data. And then in part 2, we'll actually show you how to implement these options with pandas. As you are already aware of, real-world datasets are often going to be missing data for a wide variety of reasons. Unfortunately, many machine learning models and statistical methods cannot work with missing data points. They require some number to be there. So, if that's the case, we need to decide what to do with the missing data. And it's important to note that when you're actually reading in missing values with pandas, it's going to display them as NaN values, which stands for not a number. It should also be noted that newer versions of pandas actually have some specialized null pandas values, such as pd.nat, meaning not a timestamp. And what's nice about this, it just implies the value missing should be of a particular data type, such as a timestamp. So for example, if you read in a bunch of stock ticker data that was the price of a stock with a timestamp associated with it, and for some reason you were missing a timestamp, then the newer versions of pandas, instead of just replacing it as a standard NaN value, it would replace it as a specialized pandas NAT value. in order to just display the fact that we know this data is missing, but we also know that it should be some timestamp of some sort. For our use cases, we don't need really to worry about what actual NaN type here. There's a deeper discussion of it inside the Lecture Jupyter Notebook, but really we just need to worry about the 3 options and the 3 method calls to use within Pandas. So the options for dealing with missing data are to simply keep the missing data, remove the missing data, or replace the missing data. And it should also be noted that later on in the feature engineering section, we're going to have a deeper discussion of how to choose these options depending on the situation. However, a really common question I get from students is, hey, I have this particular data set. Which options should I choose? And you should know there's never a 100% correct approach that applies to all circumstances. It really depends on the exact situation you encounter and what trade-offs you're willing to make. Each of these options has its pros and its cons. So let's discuss these options in more detail. Let's start with discussing keeping the missing data as is. Basically, if you're missing a data point and it shows up as not a number within Pandas DataFrame, you just go ahead and leave it be as not a number. So the pros is this is the easiest to do. You just read in the data and that's it. You're pretty much done. And the other pro is that it does not manipulate or change the true data. Your data set was missing a value, and so whenever you're going to use it, you're going to report that it's missing that value. So what are the cons here? Well, unfortunately, many methods do not support a not a null value. Some machine learning methods do, but many do not. They require some sort of number to be there. And the other con is there's often going to be a reasonable guess for filling in that missing data. A really common situation as well is if a data set or data cell happens to be a true value of 0, sometimes an entry system would just log it as a NaN value. For example, if we're dealing with a grocery store that sells products and maybe they are having a giveaway, so they sold the product at a free price, instead of setting the price at 0, maybe they accidentally set it to just missing a price value, since it was technically no price and they were giving it away for free. So in those kind of situations, it's totally reasonable and actually correct to just set the price to 0. So again, depends on the exact situation of when it makes sense to just keep the missing data versus trying to put in a reasonable guess. So pros with keeping the missing data, very easy to do, doesn't manipulate or change anything. So now let's talk about dropping or removing the missing data. The pro to this one is that it's also relatively easy to do. Pandas makes it really easy to either drop a row that's missing some data or drop an entire column or feature that happens to be missing a lot of data points. And what's also nice about this is with Pandas, you can base this on rules. For example, you could drop a row that's missing 2 data points or 3 data points or 4 data points, etc. So what are the cons here? Well, as soon as you start dropping or removing data from your data set, you have the potential to lose a lot of data or potentially useful information. And what's going to do is that also limits trained models for future data. For example, if your current data set is missing a lot of information on a particular feature or column, let's say it's missing data on the weather for a particular day. So you have a bunch of rows and one of the features is the weather for that particular day. And at your particular time point that you're running these machine learning models, you are missing a lot of data on this particular column. So if you just decide to drop that feature column and then you train your machine learning model, if in the future you actually start collecting that weather data and you don't have it missing all the time, unfortunately, your previous model was not trained on weather data. So now you have to decide, do I just throw all that data away and start retraining on my new data sets where I am keeping track of the weather, or do I just never take weather into consideration? So it limits the trained models for future data. And again, we'll discuss that particular point when we talk about feature engineering in a feature section of this course. So just keep that in mind. This one's a little more complicated with that trained model capability. So I want to talk about a little more about dropping a row versus dropping a column or feature. So when should we think about dropping a row? Here we can see we have these countries. Each country is a row, and then we have features of that country, such as the year, population, GDP, and area. And in this particular situation, it probably makes sense to drop a row when a lot of information about that particular row is missing. So we can see here for United States, we only have the year. We're missing population, GDP, area. For this particular case, it wouldn't make sense to drop population, GDP, and area because we have that information for all the other rows except for USA. And in this particular situation, we're going to pretend that we can't just look up population, GDP, and area. So here, it makes sense to drop the row for USA because we're missing a lot of information just for that row. Downside is we are losing what could be a potentially valid data point, but in this case, there's not really any predictive information here because most of it was missing to begin with. So we should probably just remove USA because clearly this data point as a row should be dropped. It doesn't have any useful information in it. It's often a good idea to calculate a percentage of what data is dropped. So for example, here, if we drop United States, we're actually dropping a third of all our data, 33%. That's pretty high because this is such a small data set. But you can imagine if we had 200 countries, it's not a big deal to just drop one of them. Now, let's talk about dropping a feature column. Dropping a feature column is a good choice if every row or most rows are missing that particular value. So now you'll note we have a different situation where we have a lot of information for all the countries, except for some reason, only a few countries have information about that area column. So in this case, it would make sense to drop the column instead of dropping rows United States and Canada. Because USA and Canada, we actually have a lot of information about them. It just so happens to be that we're missing the area. And in conjunction with that, it looks like we're missing the area for multiple countries. So in this kind of simplified case, it would make more sense to drop the area column instead of dropping both USA and Canada rows. Finally, let's talk about the more complex situation where we decide to fill in the missing data. And the pros here is that this has the potential to save a lot of data points for use in training a model. However, what are the cons? This is the hardest to do, and importantly, it's somewhat arbitrary. At the end of the day, if you're filling in missing data with some sort of statistical estimation, you are, in fact, just making up a number. Now, it could be a very reasonable number to make up, given the statistical estimation method you're using, but it does have the potential to lead to false conclusions. So you should always be very careful with the reasoning you're using on filling in that missing data point. So, for example, what if we are filling in missing data where we want to fill with the same value? So here I have a situation for my data set where I have different countries, the year, the population, GDP, and now this other column here is called carriers, and it stands for how many aircraft carriers are present in the country's navy. And in this particular case, what happened is Canada and Mexico don't have any aircraft carriers in their navy for this particular data set. So instead of filling it in with 0, the data set shows as not a number, as in not relevant because there are no aircraft carriers. So it's a really good choice to replace nan if it was just a placeholder for something like 0. So again, with that grocery price example that we talked about earlier, it's a good idea to just say, hey, all these null values, they're actually just place markers or placeholders for 0, since there are no aircraft carriers for that particular country. In this case, this is a great situation to fill in the missing data, and you just say, hey, this was a placeholder for 0. Now, obviously, that takes some domain experience and a little bit of research to make sure that this is a valid choice. Now, there's the other option of filling it in with an interpolated or estimated value. And again, this is kind of one of those harder or more complex decisions to make. So this requires a lot of reasonable assumptions and a lot of domain experience. So this last column represents some percentage of something. And often in data sets, you may try to fill this in, maybe even using interpolation. So you can see here it goes from 25% to 75%. And maybe you're thinking Canada is somewhere in between Mexico and USA. We're actually not defining what percentages here on purpose. So in your data set, it could be a reasonable assumption to say, okay, I think Canada's percentage value of some feature should be between Mexico and USA. So then you could interpolate it between 25 and 75 and say 50% is the correct percentage here. Again, this is a totally made up feature. Percent doesn't really mean anything here. But if you have enough domain experience to say it's not unreasonable to say Canada's percentage is in between Mexico and USA's, you could fill it in with interpolation. Again, this is much harder, requires reasonable assumptions. And at the end of the day, we are technically just making up data for Canada here. Okay, so what we're going to do in part 2 is explore the code syntax in Pandas for dealing with missing values. And later on in the course, when we talk about feature engineering, especially as part of a larger machine learning project, we're going to have a deeper discussion on trying to decide between keeping, removing, and replacing options for a real data set. So just keep that in mind. We're really going to talk about the mechanics of how to do these options with Pandas. Later on, we'll actually show you a real-world discussion on what option we should choose. We're going to head straight to the Jupyter Notebook and show you how to either keep missing data, replace missing data, or drop missing data, all with Pandas. Let's head to that Jupyter Notebook. Okay, here we are in the Jupyter Notebook. I've already imported NumPy as NP and Pandas as PD. As a quick note, with the version of Pandas that we're using for this course environment, we're going to use np.nan to display a null value, essentially saying this is not a number, we don't know what it is, it's missing. But newer versions of Pandas will have pd.na, which is a new Pandas value, and there's a little bit of description inside the lecture notebook with a link to the GitHub issue. This is probably going to be in the future the way they indicate missing data. And there's also specialized versions like NAT to symbolize that the value that is missing should be a timestamp of some sort. But for right now, we're really just going to focus on np.nan, since when we read in data, that's the way it's going to be displayed. So the second thing I want to focus on is that typical comparisons should be avoided with missing values. And there's 2 great links inside your lecture notebook, which give a little more explanation than what we're going to show here. But essentially, when I mean that typical comparisons should be avoided, if you say np.nan and check for equality with np.nan, often beginners will think that this should be true. But in reality, it's actually false. And the general logic here is that since you don't know truly what this value is, it should be missing, and you also don't know what this value is, it's missing, there's no way you can actually tell if these 2 missing values are going to be equal to each other. So it says they are false. However, if you are checking for some value to be nan or not, you have to say np.nan is np.nan, and then that will return true. So if you have some variable that for some reason is missing, you should be using my variable is np.nan to check whether or not it's actually a missing value. Don't actually use equality here for the reasons stated earlier. Okay, so next, let's go ahead and read in a data set that has some missing values. I'll say df is equal to pd.readcsv, and this data set, it's in the Pandas folder. It's simply called moviescores.csv. And if we check out this data frame, notice we have some information. We have actors here, first name, last name. So first name of the actor, Tom Hanks, the age of that actor, the sex of that actor. And then we went ahead and did a survey here. So essentially, people were asked to score their opinions of actors from a 1 to 10 scale before and after watching one of their movies. However, some data is missing. So here we have Tom Hanks, 63, male, and the pre-movie score for this survey was 8. And then after watching a Tom Hanks movie, they decided to score him 10. You'll notice this second row at index 1 is missing all the values. And then you'll notice Hugh Jackman, it looks like for this particular survey, we didn't actually have a pre-movie score or post-movie score. So we didn't actually show any movies here. And then Oprah Winfrey and Emma Stone, you'll see that those are fully informed. Okay, so let's go ahead and show you how to check and select for null values. One way to do this is by saying df is null. And what this method does is it simply returns a Boolean, true or false, if you have a null value. So notice true for every item in row 1, where they were all null values. And then Hugh Jackman, row 2, we have true because he didn't have a pre-movie score or post-movie score. If you want to check for the opposite, you can say df not null. Run that, and then you'll get essentially the opposite of that. It's going to give you false if it is a null value, and true if it's not a null value. Okay, so as you can imagine, we can start using actual columns and this not null or is null method calls to select rows based off whether or not it's missing that value. So for example, let's go ahead and check out all the actors where we're not missing their pre-movie score. So that's going to be Tom Hanks, Oprah Winfrey, and Emma Stone. What we can do here is say DF and then select that column, the pre-movie score, and then say not null. And now we have Booleans associated with each row. So I know that I have a pre-movie score for row 0, 3, and 4, which then I simply pass this in, just as we've done before with conditional filtering. And then I only get back the rows where I have a pre-movie score. So you can use these not null and is null conditional filtering to only select columns where certain features are present. Okay, so another example is, let's say I was only looking for an actor where the pre-movie score was missing and then their sex was also not null. What I could do here is just combine these. So say pre-movie score is null. Recall it's Hugh Jackman. So if I just pass this in, I say pre-movie score is null, that's Hugh Jackman, and it's also the row that's missing everything. So there's 2 here that are returned. So this row that's missing everything, and then Hugh Jackman. And let's say I want to add in another condition, maybe where we actually know the first name. So I don't have to worry about these rows where I don't even know the actor's name. I can combine conditions just as before. I'm going to zoom out just a little bit so we can see this. We just wrap this condition in parentheses and then say and then parentheses here I'll say where first name is not null. So just as before, this is conditional filtering, except now we're using method calls on these columns. And this is essentially asking me or asking Pandas to return where is the pre-movie score null and where I also know the first name. So the first name is not null. And so when you run that, you only get back Hugh Jackman, which makes sense. Okay, so now that we're familiar with the is null and not null methods, as well as how to do conditional filtering based off if something is null or not null, let's talk about the 3 options we had, which were to keep the data, drop the data, or fill the data. So keep the data, that one's really easy. You just say df, read in the data, and then if it's missing, you just go ahead and keep it in. Okay, so keep the data, pretty much done with that one. You just read in the data set, keep any missing values, and then you're done. So let's move on to dropping the data. And there is a drop NA call, and I would highly recommend that you call help on df drop NA. And then it's actually going to show you some really nice examples here of how it works, as well as the important parameters. And the important parameters are really axes, essentially saying, are you going to drop based off rows or based off columns? How are you going to drop it if you have any cells missing or any values missing or all those values missing? And then also the threshold, which is going to require that many non-null values. And then you also have the subset argument, which is going to allow you to only consider certain columns. So let's kind of build up on these different parameters. And what's nice here is they're actually showing you an example here of this data frame, as well as how to quickly build in that data frame. And what we're going to do here is say, take my data frame, and then I'm just going to say drop NA. And if you just say drop NA, essentially what it's going to do is it's going to drop any rows that have any missing values. So you run that, and you get rid of that row that had all those missing values, as well as Hugh Jackman, where he didn't have those movie scores. But let's imagine we only wanted to drop that row that was missing all those values. What I can then do is use this threshold argument. And again, the threshold, sometimes a little tricky to understand, but all it's saying is I require that many non-null or non-NA values. So if I come back here and say threshold is 1, that basically says go ahead and drop any rows that contain null values unless they have at least one non-null value, which that means when I run this, I see Hugh Jackman again, even though he's missing his pre-movie score and post-movie score, he has at least one non-null value, such as his name. And I can keep raising this. I can say 4 here. And you notice Hugh Jackman still shows up because we have his first name, last name, age, and sex. But if I raise this to 5, he gets dropped because he doesn't have at least 5 non-null values. Okay. So that's a way to kind of distinguish dropping something that's missing all the values versus we have at least some information on them. Nice way to essentially remove rows that are just missing everything. Now let's also talk about the axes argument. If I say df drop NA and I say axis is equal to 1, you'll notice by default, if I do shift tab here, axis is equal to 0, meaning it's focused on the rows. If I say axis is equal to 1, it drops everything. So why is that? Well, now it's considering based off columns. So it's essentially saying in our original data frame, here we have basically values where we have columns that are missing values. And you'll notice that every single column has at least one instance of a missing value. First name has a missing value in the column, last name, etc. And it's really because of this row 1. So if I say axis equal to 1, instead of dropping rows, it's going to say, okay, drop columns that are missing any values. So that's all the columns. All the columns have missing values here. So typically when we're dropping things based off null values, especially with the way we organize our data, where rows are data points and columns are feature, we're just going to leave default axis is equal to 0. Because that's really typically the way we're thinking about this. Okay, so as you can imagine, you can use the threshold argument to essentially filter out based off any conditions you want. And the last important argument to show you is the subset argument, which is basically only going to consider certain columns. So define in which columns to look for missing values. Here they're using subset, so let's go ahead and do that. We see df here, and then what we can say is df drop NA. That removes everything that's missing any values based off the rows. But if I say subset, and we pass in a list of columns to consider, such as last name, and we run that, you'll notice Hugh Jackman now shows up instead of being dropped as before. So if I say df just drop NA, it drops Hugh Jackman. But if I say subset, it's basically only going to consider the last name column. And there was only one row that was missing the last name. That was this number 1 row. So you can use combinations of subset and threshold to filter out based off whatever columns you're concerned with that are missing values. Okay, so we now know how to drop values as well as how to set conditions for what values should be dropped. But now let's move on to actually filling in the data. And this is kind of the hardest one to really consider because you have to have a reasonable choice here. So if I say df, I can call fill NA. And again, I would encourage you to call help.fillNA and check out the documentation here where it's showing you examples of how to fill NA. But something to note here is that right off the bat, you could just say df fill NA and then just provide a single value that would fill in every single missing point. So I'm just going to provide a string here saying new value exclamation mark. So note we have first name, age, and so on, pre-movie score. And if I just say fill NA to a new value, it automatically fills in this string to wherever we had stuff that was missing. Now typically this is not what you're going to do because now I'm replacing strings where something should have been probably a numeric like 63 or 51. And so what Pandas ends up doing is if you start filling in strings for columns that should have been numeric, it's going to start making this 63 into a string instead of a floating point value or integer value. So while this is possible of saying fill NA, typically we don't just say one value. Instead, we grab the column we're interested in filling. So, for example, if I wanted to select pre-movie score and wherever that's missing a value, go ahead and fill it in with zeros, I would say df pre-movie score and then call fill NA here with 0. And so now you'll notice that there's zeros here instead. And if I wanted to make this change permanent, all I would need to do is assign this change. Take in the current pre-movie score. If there's a missing value, fill it with 0, and then that's my new column. Now I'm not going to run this to show you a couple more examples, but hopefully you get the idea that you can do this typically at a level. So for example, if I didn't know the sex, but maybe I assumed anyone with missing sex was male, I could say fill NA with the string M. And one of the most common questions I get then from students is, I don't want to fill in by just some arbitrary value like 0. I actually want to fill in based off a function, like the mean. Well, that's actually quite easy to do. So if we take a look at pre-movie score again, notice I didn't run that cell, so I still have the null values. You can simply read in the DataFrame CSV file again if you accidentally ran that. But let's say I want to fill in these null values with the average pre-movie score. Well, what do we do here? We can simply say df pre-movie score dot mean. And what's nice about dot mean is it's going to give you the average based off the existing values. So it's only looking at 6, 7, and 8. And the average of these three should kind of obviously be the center value, 7. So that's the mean value. And so what we can do is say df pre-movie score dot mean, and then say dot fill NA with the mean value. And when you run that, you'll notice that these 2 points that were missing are now filled with the average value. And sometimes if you have a pure numeric column, what you can do is say df fill NA with df mean, open close parentheses, and that will attempt to automatically fill everything with the averages. Now, does this make sense sometimes? Maybe. It probably makes sense for something like pre-movie score, where you just assume that people have some sort of average feeling towards an actor, but it probably doesn't make sense to start doing things like fill in with the average age. What is nice about this method of just calling it on the entire data frame is for things that don't have an average value, there's no average value for the first name, it just went ahead and kept it as null values. So it's kind of like a quick and dirty way to fill in things. And finally, the last thing we'll show you for filling in missing values is with the interpolate method for interpolation. Now, we're typically not going to actually use something as direct as this, but I do want to show you that this method exists. We'll show you kind of some more sophisticated ways of doing this within the feature engineering section. But I'm just going to copy and paste this dictionary from the lecture notebook and then turn this into a series by saying series is equal to pd.series, airline ticks. I run that and I get my series. So as I mentioned before, sometimes you want to interpolate. Is this a good situation for interpolation? Probably, because I can see these are airline ticket prices where economy is $30, economy plus is at $50. I'm missing the business value price class, and then there's first class at $100. So it might make sense to try to interpolate this, assuming it's already in the correct order. Again, that's kind of a big assumption here, but I could interpolate missing values. And what it does is it just does a linear interpolation from the point above and the point below. So it's going to fill this in with a linear interpolation between 50 and 100, which is essentially the average between 150, which is going to be 75. And for that, you simply say interpolate. And then it fills it in with the interpolation. Again, we're really not going to do this too often because you have to do a lot of assumptions here as far as the ordering of your data, but technically you could sort by maybe another column and then start the interpolation process that way. There's a link to the full docs on the method. You can also just kind of do Shift Tab here to explore the documentation inside your Jupyter Notebook. But as I mentioned, we're going to show you some more sophisticated ways of filling in missing data when we talk about feature engineering, essentially using values from other feature columns to fill in the data. All you need to understand from this lecture is that you have a couple of method calls that you should know. So after this lecture, the main things to take away is the fact that you shouldn't be doing comparisons on null values with equality. Instead, use is. And then there is the is null method as well as the not null method available to you. And then finally, there is drop NA available to you, as well as, if we scroll down here, the fill NA method. Thanks, and I'll see you at the next lecture. Welcome back, everyone, to this discussion on GroupBy Operations, along with a discussion on the multi-level index in Pandas. A GroupBy operation call allows us to examine data on a per category basis. So that means being able to answer questions like, what's the average per group or per category? Or how many rows do we have per category? So let's explore what this looks like in Pandas and what we mean when we talk about per category. Here we have two feature columns in this so-called data frame. We have a category column and a data value. And so when we're performing a group by call, essentially what we want to do is aggregate a continuous value per category. So here, the first step is to choose a categorical column to call with group by. And categorical columns are non-continuous. Essentially means that you have distinct groupings. So this category column has three distinct categories, A, B, and C. Unlike the continuous data value column, where we can see it's just some sort of continuous numeric call. Now, often beginners are confused and they think that categorical columns must be a string column. While it's more common for them to be string columns, keep in mind that they can actually still be numerical. So for example, the cabin class category on a ship or a plane, like first class, second class, or third class, those could just be represented as numbers 1, 2, and 3. Another example could be the model year for a dataset consisting of cars. You can have the category of 1970, 1971, 1972, and so on, just different years. So keep that in mind. Once you've decided on the categorical column, then what you do is you call a GroupBy call on that. And it has to be combined with an aggregate function call. So what we do here is what Pandas is actually doing under the hood is it takes in your data frame, and then once you decide on the category to group by, you essentially separate out all the other columns by the distinct categories. So we have all the data values for A, B, and C here. And then you decide on an aggregate function. For example, if we call the sum aggregate function, it's going to take the sum per category, essentially summing up all the A values, B values, and C values. So you can see the result here for A is 10 plus 5, 15, 2 plus 4, 6 for B, and then for C we have 12 plus 6 is 18. You could call a different aggregate function, such as the mean, so then it grabs the average value per category. And then you can have something like the count, essentially asking how many rows are there per category. This is different than sum because it's just asking you to count the instances per category. And in this case, they're all the same. There's 2 rows or 2 instances per category. So note that in Pandas, calling just GroupBy by itself creates what's known as a lazy GroupBy object because it's waiting still to be evaluated by an aggregate method call. Let's explore this all further in Pandas in a Jupyter notebook. Okay, here I am in my Jupyter notebook. I've already imported NumPy and Pandas, and the data set I'm going to read is located within the Pandas folder. So we're going to say read CSV, and it's called mpg.csv. And this data set just has a bunch of information for lots of different cars. The miles per gallon, number of cylinders in their engine, displacement, horsepower, weight, acceleration, and then there's a model year, an origin number, and then the name of the actual model of the car. So what we're going to do is let's go ahead and start exploring how maybe performance has changed for the cars throughout the years. You'll notice that we first have to decide on what's the categorical column. So categorical column here could be something like model year. We have multiple instances of various cars per year. So maybe we're trying to answer the question, how has performance of miles per gallon changed throughout the years? So we could say, go ahead and grab the average miles per gallon for the years, like 1970, 1971, 72, and so on. Okay, so keep in mind this does take a little bit of knowledge of your data set to decide on what is a categorical column versus a continuous one. Another example of a categorical column here could be something like cylinders, because it looks like we have multiple instances of 8-cylinder engines, 4-cylinder engines, and so on. An easy way to check for this is to do something like, for instance, model year. And you could just ask for the unique values here. And you could see that there are multiple instances of 70 based off what you see in the actual series. And then you can see there's unique here. You can also do something that we've done before, which is value counts, which goes ahead and gives you the actual number of rows per category. It's kind of a very fast group by, but we'll show you how to do this manually in just a second. Okay, so we decided on our categorical column, which is the model year column, because I'm trying to answer a question like, how has miles per gallon changed on average per year? So then what we need to do is say df group by, and then you're going to group by and pass in what you want to group by. In this case, it's called model year. Now, I did mention that group by objects are lazy, and that means that if I just run group by model year, I get back this group by object. And what this means when I use the term lazy is Pandas hasn't actually done any work yet because it's still waiting on performing the calculations from the aggregate call. So it's still waiting for you to say, do you want the sum per category, the mean per category, etc. So what I can do here is say call.mean, and keep in mind there's a list of all the aggregate method calls in the Jupyter Notebook as well as in the documentation. So if we take a quick look at the Jupyter Notebook for this lecture, if we scroll down here, we see the GroupBy method. I have a list here of all the most common options of things you may want to aggregate by, as well as the link to the documentation on this. But let's go ahead and back to grabbing the mean value per model year. So note what this is doing. Suddenly, the model year is now the index. So what it's going to do is it's going to grab the column you want. It's going to group by that particular category, set that as the index, and then it takes in the aggregate of what it can do. So if we come back here, you'll notice, if we say DF, we had a name column, and there's no way we can take the average of things like Chevrolet, Buick, and Plymouth, etc. So instead, it just doesn't bother to return that column. It's going to return back pretty much the numeric columns that it can perform a mean aggregation on. So here we can see MPG. You'll also notice that this is essentially a data frame that's being returned here with a named index. So if I was only interested in MPG, I could then, simply using brackets, grab the MPG column off this returned data frame. And so now I can see the average MPG per model year. And you can see that in the 70s, it starts off 17, 21, 18. But as you move further in time through the 80s, the miles per gallon starts to get higher, which is just a general trend that miles per gallon has typically gotten higher over time. Obviously, it may depend on the actual type of or model of car. Speaking of which, sometimes you want to actually group by multiple columns. So I mentioned that maybe miles per gallon is different by type of car, such as the number of cylinders in that particular car's engine. So what we could do, instead of just grouping by a single column to get the average, what I could also do is group by the number of cylinders as well. So technically, I could say DF, group by, and then pass in a list. So I'll first group by model year, and then after that, I'll group by the number of cylinders. And then let's calculate the average value there. And notice we start to have what's known as a multi-level or hierarchy index, meaning model year and cylinders are not column names. And this is displayed to you by the fact that they're on this second line. The columns I currently have in this data frame that's being returned here are MPG, displacement, weight, acceleration, and origin. And we can confirm that by simply calling columns on the return data frame. And I see MPG, displacement, weight, acceleration, origin. However, if I take a look at my index, I have two levels of an index. I have this model year level and then the cylinders available for that model year. So it's grouping first by model year, so 1970, and then per cylinders. So I can see that the 4-cylinder engines had higher miles per gallon than the 8-cylinder engines. And then I can actually now start doing a comparison, not just per year, but per cylinders per year. So now I'm kind of adjusting for multiple categories, which makes sense because then I could do things like just compare 4 cylinders from 1970 on average to, if we scroll all the way down, 4 cylinders in 1982 on average. Again, higher. Okay, so the thing to keep in mind here is this has returned a multi-level index. So if I call index, I see here that it's trying to say that it's a multi-index with these tuples. So there's the outer index of 70 and then 4 cylinders. Then there's another instance of 70 with 6 cylinders, 8 cylinders, and so on. So let's talk about how to deal with and work with something that returns back a multi-level index, because it's going to be a bit trickier to try to grab something like MPG just for 1970 with cylinders of 6. And as before, I could just grab every instance in a column by saying something like MPG. So again, now I have this kind of multi-index series here. Okay, so before we move on, I just want to quickly also show you that instead of just calling mean or sum at once, you could also do something like describe, which is DF group by, let's go ahead and just do model year. I could say describe, a method we've seen before. And so what this does is it shows you everything here, miles per gallon, the count for that, mean, standard deviation, min, percentiles, etc. Sometimes it's easier to read this if you transpose it. as I've mentioned before. And so what this does is it returns back this slightly complicated data frame, but it essentially shows you all the aggregation methods possible for a single column. So if I was interested in what is the average miles per gallon for 1971, I would come to 1971 model year, miles per gallon, average, and it's 21.25. I can also see the minimum miles per gallon value as well as the maximum miles per gallon value for each of these years. So just something to keep in mind in case you want to just quickly grab some statistical analysis of a data frame. But I mentioned that we kind of want to focus on this idea of this multi-level index and then how to deal with this multi-index object. So let's say year CYL for cylinder is equal to DF. I will call GroupBy. And again, we're going to group it not just by model year. Notice I'm passing a list in here, but also by cylinders. And then let's just grab the average value just so it's not overwhelming. So now that I've assigned this to a data frame, I can take a look at it. And here's what we had before. Essentially the average of miles per gallon, displacement, weight, acceleration, origin, etc. And then it's the average, not just per year, but also per cylinders. So we just explored the index, and I can actually grab the index names, which is model year and cylinders, by calling .index.names. And so reports back model year and cylinders. And this can also then report back the levels available. So if we say index.levels, it gives you the outer levels. Notice it's a list of lists, multi-dimensional array here. And we have the levels for the outer level index, which is the model year, and then the possible cylinders. Essentially showing you all the possible years and all the possible cylinder values. Keep in mind, not every cylinder value is present for every year. So there are no 3-cylinder cars for 1970, for example. Okay. So let's talk about now working with this index. What I can do is I can grab based off the outside index using .loc, just as I could with a normal data frame. So if I have this year cylinder, and let's go ahead and imagine that I'm only interested in grabbing on this outside model year for the year 70, I can simply say .loc 70, and the .loc commands are going to work in reference to the most outside level index. So then this returns back the values for 1970. Keep in mind it just drops that outside level index, so then you only see cylinders. What I could also do is then pass in a list here. For example, I could then say, okay, give me 70, comma, and then also as, let's say, 82, the last year value. And since I'm asking for more than one year in order to distinguish, it's going to include model year as the outside level index here. So then I could say, okay, let's check out cylinders for 25 miles per gallon versus in 1982, cylinders for 32 miles per gallon. So .loc, it's going to work on this outside level index. If you only wanted to grab a very particular row, for example, let's say I want 8-cylinder cars for the year 1970, then you're going to say year, cylinder, .loc, but then you're actually going to pass in a tuple. And a tuple essentially corresponds to the output we saw earlier when I called .index. Notice there were these tuples here. Well, all I need to do is, for example, grab one of them, like 4-cylinder cars for 1970, and then pass it in here, and it returns back that exact row as a series. Previously that we saw, if I say group by, and then I use 2 or more columns, and then perform some sort of aggregate operation, what happens is we go ahead and run this, and I check out year cylinder. I have this multi-level index. I have the model year level on the outside, and then the cylinders level on the inside. So again, this index is labeled model year, outer level, cylinders, inner level. And technically you can have more than just 2 levels. And you can see .index.levels reports back the options for each level. And then we saw that the multi-index actually gives you these tuple pairings, or if there's more than 2 items, if you have more than 2 levels. But essentially, we can see we have 4 cylinders for 1970 row, 6 cylinders for 1970 row, and so on. And if you want to grab just one of these rows, like 1982 6 cylinders and just grab this highlighted row there. Then what you do is you just say .loc, and as a tuple, you can provide that tuple pairing. Okay, but now let's go ahead and move on and talk about using something called a cross-section, which is a more general purpose way of grabbing something that has this multi-level index. And the method call is .xs. So what I'm going to do is quickly take a look at year cylinder. I can see it right here. I have model year and cylinders, and then I'm going to call .xs, which is, if we take a look at here, it's a cross-section. So essentially what this does is it takes in a key, an optional axis. By default, we'll keep it at 0, since that just means look at the rows, and we want to have our multi-index levels on the rows. And then we can also see that we have this level option. And the level just refers to what actual index you're looking at. So are we looking at the model year level or the cylinders level? So let's imagine I wanted to grab just model year for 1970. The way this works is we provide a key. In this case, the key is actually just the integer, 70. And then I have to tell it what level I'm looking at. So I'll say, I'm looking at the level model underscore year. And if I run this, I get back that subsection here for that particular key at this particular level. Something to keep in mind is when you're using cross-section, it only takes in a single key as the value. So if you wanted to try something like 70, 80, this actually wouldn't work. So if you run that, it's going to say key error. I can't find 70, 80 as a key. So you can't actually pass in a list to get multi-levels. Instead, if you were dealing with this data frame and for some reason you wanted the year 1970 and the year 1980, as we showed you in the previous lecture, you just call .loc and then pass in that list of options. You'll say, okay, give me 70 and give me 80 as a list. Run that, and it works automatically here on the outside index. So if I had the capability to already use .loc, what's the use of cross-section? Well, what I don't know how to do so far is grab something based off this inside index. For example, let's imagine I wanted to grab only the 4-cylinder cars, but I wanted to do it for every single year. I can't really do that easily with .loc. Instead, that's where we're going to use this cross-section tool. So what I'll do here, let me just run year cylinders so we can see it. Again, what I'm looking for are the instances of 4 cylinders for every single year. So I want this first row here, then I want this next row, then this middle row here, etc. So I say cross-section, XS, and the key I'm looking for is 4 cylinders. However, I just need to let cross-section know that the level I'm looking at is this cylinders level. So I copy and paste that here. And then when we run this, I get back this nice data frame that shows me the model year and then the values. Something to keep in mind is that when you're asking for a particular level, like cylinders, or up here, we're asking for the level model year, that actual level then is not shown in the results because there is only one attribute or one value for that level. So what I mean by that is the reason we're not seeing model year here is because they're all the same. It's all 1970 or 70. And the reason we're not seeing cylinders in this output is because it's all the same. It's 4 cylinders. So just keep that in mind. If I just look at this data frame on its own without knowing the code that produced it, I actually have no way of telling what cylinders this is referring to. So when I actually assign this to some sort of variable, I would probably want to say something like 4 cylinder is equal to, etc. Because the key itself is not super apparent what I chose in the actual output. So just a little tip to keep in mind as you're working with this. And then another thing I want to know is people then ask, rightly so, if I'm looking at year cylinder, and let's say I actually want the cylinders for 6 and 8 for every single year. Well, that leaves us in a bit of a conundrum because I just told you we can only put one value as the key. And if you're trying to then select certain cylinders, then it's probably much easier to filter out those values before you run the GroupBy call. So you should always keep in mind that what actual values are you looking for in the final results. And if since the beginning you were only interested in the cylinders for 6 and 8, then you should filter that out in the original data frame first and then just call your GroupBy. That's going to be a lot easier to both do and read than trying to mess around with .loc and that cross-section to get those results. So, for example, if you only want the aggregate for cylinders 6 and 8 for every year, what you should do is just before you even call GroupBy, say, okay, give me DataFrame, where DataFrame of cylinders is in, and then you pass in the options you're looking for, like 6 and 8. And so now we see here our DataFrame where we only have 6 and 8 cylinder cars. Once you've done that filter, then go ahead and call GroupBy cylinders or model year or whatever you're looking for. So in this case, we can go ahead and just do both, model year and then cylinders, and then grab the mean that way. So this gives you that result of only 6 and 8 cylinders for that particular model year. So a lot of times I see beginning students get confused. They're trying to figure out how to do something like this using .loc or .cross-section when it's actually just a lot easier to filter out your data frame first and then call GroupBy on what you want. So always try to keep that in mind as far as what's the simplest way to get the final results you're looking for. And often you'll find it's a lot easier to do the filtering and conditional filtering on the data frame first and then do your aggregate functions. Okay. So finally, what I want to show you are things like swapping the levels and sorting the multi-level index. So for example, we come over here. I still have this year cylinder object, and currently the outer level is model year, inner level is cylinders. Technically, I think that makes the most sense, but if for some reason you wanted to swap these, make cylinders the outer level and model year the inner level, all you need to do is say swap level, open close parentheses, and it will swap it for you. So we can see here now cylinders is on the outside and model year is on the inside. Whether or not that's useful kind of depends on the situation, but it is available for you to swap the levels. Okay. And then finally, let's go ahead and show you how to sort the multi-level index. So right now it's sorted model year from earliest model year to the latest model year, but if you wanted it in descending order, starting from the most recent to the bottom, then actually all you need to do is just before say sort index, and then you can specify which index you actually want to sort by. So for example, I can say the index I want to sort by, the level is model year level, and I actually want it with ascending is equal to false. So it's the same command or same method that we saw earlier, except now we actually just provide the level parameter that we're dealing with. So you run that, and you can see now we have it in descending order. Something to keep in mind, if you start looking at inside levels and start sorting by that, then you may start breaking up this grouping. For example, if we say cylinders, ascending is false, you'll notice suddenly it breaks that relationship because you have 8 cylinders for multiple years. So just keep that in mind. Usually when you're sorting, it makes sense to sort by the most outer level. Last thing I'm going to show you in this particular method is a more advanced method that allows you to customize what aggregate functions you want per category. It's a pretty neat advanced feature. We won't really see it too often, but hopefully in your own work, you may find it helpful sometimes. So let's jump back and take a look at our original data frame. And as I mentioned before, when we're thinking about doing GroupBy, we've just been applying the same aggregate function to every single column here. So we did the mean of MPG, mean of cylinders, displacement, horsepower, weight, etc., depending on what you actually choose to group by. But sometimes it doesn't actually make sense to do the same aggregate function on every single column. So what I want to show you is how you can actually specify a particular aggregate function or group of aggregate functions for a particular column. And the way you do that is through the .agg, which is the generalized aggregation method. So we'll say df.agg, and this is then going to aggregate, and it can actually take in a list of string calls. And the string calls are going to match up with the method name in the table in the lecture notebook. So recall in that lecture notebook, let me just bring it in here real quick. At the very top of it, I mentioned, scroll all the way to the top, that there are some common options here. There's also a link to the online documentation. But you'll notice we have mean, sum, size, count, etc. So the string calls you're about to see me type in, they come from this list of common options. But what I really want to show you here is with the aggregate method, you can essentially say, okay, give me the mean of the MPG column, but the standard deviation of another column. So to show you how this is run, let's first do it on all the columns, and then we'll show you how to pass in the dictionary. So on all the columns, if I wanted mean and standard deviation, here inside of this add call, let me zoom in one level here. Inside of this add call, I say, give me the standard deviation and the mean. And then I run that, I see aggregation, standard deviation, and mean. And here it is as the index, standard deviation, mean for all the columns. Now you'll notice that some of these don't really make sense. Standard deviation of the model year or the origin doesn't really make sense either. So some people then would take this and just filter out by what they're actually looking for, like MPG, for instance. But let's imagine that you only wanted some aggregate functions for some particular columns. Well, the way we can do this is we actually pass in a dictionary into the aggregation call. And this is this advanced method that's really useful as you start to upgrade your skills with Pandas. Now what you do here is you pass in a dictionary where the key is the column you're interested in, and then the values are a list of the methods you want to call. For example, let's imagine I wanted to call max and comma mean for the MPG column. And then as another key value pair in this dictionary, I'll go ahead and grab weight and then say, well, I'm only interested in the mean of the weights as well as the standard deviation of the weight. So note what I'm doing here. I'm actually applying specific aggregation functions to a specific column, and they actually don't need to match up with the other aggregation functions I'm passing in for another column. And when you run this, you get back this nice result where you see your columns, the original ones, MPG and weight, and you can see the max and mean for the values you're interested in, and, for example, the mean and standard deviation for the weight column. Now, keep in mind, it's going to fill in a nan value for things you didn't call. Since I didn't call standard deviation on MPG, it just fills it in as a null value. And this will often make sense depending on your particular data set. Because for whatever reason, maybe it didn't make sense to grab the max for the weight here, etc. So this is just a kind of most advanced method you can use to apply particular aggregation methods to particular columns. Okay, there's a lot more examples in the lecture notebook. We really won't actually execute something like this on our own in our projects later on in the course, but I do want you to be aware of it because it's a super powerful tool, especially when you're writing things like reports for other people, and you don't want them to start thinking, oh, why did they report some aggregate function for a column where it doesn't make sense? So this allows you to just replace it with null values if for some reason it doesn't make sense for that particular column. Okay, thanks, and I'll see you at the next lecture. Hello everyone, and welcome to the lecture for merging, joining, and concatenating data frames. In this lecture, we're going to learn how to combine data frames through a variety of methods. Instead of actually live coding everything out, since these methods and commands are actually really simple, and most of the typing is just actually creating data frames to merge or join together, what we're going to do is just walk through the lecture notebook for this lecture. It's called Merging, Joining, and Concatenating, and it's under the Pandas folder. Let's go ahead and jump to that Jupyter notebook now. All right, here we are at the Jupyter notebook for merging, joining, and concatenating. First off, we're going to create some example data frames to work with. Here, I've imported Pandas as PD, and using a dictionary and a list of index numbers, I've created 3 data frames, DF1, DF2, and DF3. If we take a look at these data frames, we'll see that we have DF1, which is columns A, B, C, and D, and indexes 0 through 3. And then DF2 has the same columns except the indices are 4 through 7, and then DF3 has the indices 8 through 11. Let's talk about concatenation. Concatenation basically glues together the data frames. Keep in mind that the dimensions should match along the axis you're trying to concatenate on. For this, you just use pd.concat and then pass in a list of the data frames to concatenate together. Here, I'm going to concatenate data frames 1, 2, and 3 by passing them into a list into the pd.concat function. Here we can see that by default, the axis to join on is 0, meaning it's going to join the rows together. And we see here that this successfully concatenated, or basically glued together, the data frames. And we can see now we have A, B, and C, and D as columns with the indices 0 all the way up to 11, with each of the data points lining up nicely. Now you can also specify axis is equal to 1 if you wanted to join and merge along the columns or concatenate along the columns. And this is an example of what happens when you use pd.concat on these 3 data frames along axis is equal to 1. Notice here we have a bunch of missing values, and that's because these data frames didn't have values for all the indices that you wanted to concatenate on. For example, with data frame 1, A, B, and C, and D, you had index values for 0 through 3. However, for 4 all the way up to 11, you had no values. And that's why it filled it in with nulls when you joined this or concatenated it on data frame 2 and data frame 3. Which basically means when you're working with concatenation and pd.concat, you'll want to make sure that you have information lining up correctly when you join on the axes. In this case, we wanted to join on axis equals 0 to line everything up correctly. Had we specified to join along the columns if axis equal to 1, we'll have a bunch of missing information. Most often, you'll probably be joining columns together, so you'll in fact be joining along axis is equal to 1. However, make sure you know your data and what you actually want to concatenate before choosing an axis. Alright, let's go ahead and move along. We'll create some more example data frames, in this case, one called left and one called right. Here, if we take a look at left, we have columns A and B with some values in them, and then we have a key column, K0 through K3. We have a right data frame, which is a very similar data frame except it has different columns, C and D. However, the key column is exactly the same as the left. So I have a left data frame and a right data frame. Pandas is capable of using the merge function to do merge logic that's very similar to merging SQL tables together. And if you don't work with SQL, you don't have to worry too much about this, but I'll show you the basics of how to merge 2 data frames. You just say pd.merge and then pass in the left data frame and the right data frame, or just pass in data frame 1 or data frame 2, whatever data frames you want to merge together. By default, it will merge them on inner, and if you're unfamiliar with inner as regards to SQL merging, don't worry about it, just use the default inner. More importantly, learn about this on. Basically, when you're merging, you're going to want to merge on a key column, and you can actually pass in 1 or more key columns, which we'll see later. But basically, what's happening here is we're going to combine or merge these data frames together on this key column. And that way, instead of concatenating them, we would have 2 key columns. We can merge so that we merge them or join them on the same key column that they share. So the logic here is when you're using pd.merge, instead of just gluing the data frames together, you're going to see where the values match up on columns, in this case, the key column, and then create the rows using that key column. Let me go ahead and show you a couple more complicated examples. Here I have left and right data frames. And we'll notice here that they have 2 keys, key 1 and key 2. Otherwise, they're exactly the same as the left and right we just saw earlier. You can use pd.merge, just pass in the first data frame and the second data frame, and then you can specify on, and you can pass in a list of keys if you want to actually merge on multiple keys, such as key 1 or key 2. And here are some more examples using merge outer or merge right. Now, if you're not familiar with SQL syntax such as inner, outer, right, or left joins, don't worry about this too much. We don't actually use these in the course. We will always default to something that looks like this in the course. We just use an inner join. However, if you find yourself trying to do these sort of SQL merging and you're already familiar with SQL syntax, just know that Pandas has this how operator or parameter for you to use in case you want that extra functionality. But basically, depending if you're using outer, right, inner, etc., you may find that you have some missing values. Just keep that in mind as you're working with pd.merge. Here's an example of left. And finally, we have arrived at joining. Joining is a convenient method for combining the columns of 2 potentially differently indexed data frames into a single resulting data frame. You can essentially think of this as the same thing as merge, except the keys you want to join on are actually on your index instead of a column. So here I've created 2 data frames, left and right. Notice they have columns A, B, and then C, D, and then the index is actually the keys we're going to join on. And the syntax you can use is say left.join right. and it will automatically do an inner join between the left and the right based off of the index keys. If you wanted to merge these two data frames based off of one of their columns, you'd have to use merge. But the join method functionality comes off of one of the data frames. You say .join and then pass in the other data frame. And just like merge, you can specify how, such as inner, left, outer, etc. And remember, this is only for advanced SQL users who are already familiar with that terminology. If you're unfamiliar with that, don't worry about it too much. Let's go ahead and do a quick review of how to join, merge, and concatenate data frames, and we'll go over the key topics you should get out of this lecture. As far as merging, joining, and concatenating data frames, in order to concatenate or glue data frames together, the process is quite simple. You just say pd.concat and you pass in a list of your data frames. And then you make sure to specify the correct axis, depending if you want to join them together by their rows or by their columns. Next, you have pd.merge, and pd.merge allows you to merge data frames together, and you just pass in your first data frame you want to merge, and then your second data frame you want to merge, and then you say on, and you can pass in just a single column key, or you can pass in a list of keys. And by default, it will merge on inner. If you're unfamiliar with merging SQL tables, don't worry about this how too much. Just worry about one data frame on the left, one data frame on the right, and then on a certain key column or on a list of key columns. That's really the only functionality of PD merge that we'll be using throughout the course. And then for joining is a more advanced method for combining columns of two potentially differently indexed data frames. It's very similar to merge, except that you're actually joining on the index instead of a column. And the syntax for that is just the name of the left data frame dot join on the right. We actually won't be using join throughout the course, but I want you to be aware of it, and you can reference this notebook or the documentation in case you ever want to review joining. All right. Great job. Thanks, and I'll see you at the next lecture. Hello, everyone, and welcome to the Data Input and Output lecture. Pandas as a library has the ability to read data and write data to a wide variety of sources. For this lecture, we're going to be concerned with just four main data sources: CSV files, Excel files, HTML from the web, and SQL. In order to work with HTML files and SQL databases with Pandas, you'll need to install four libraries. The instructions are in the notebook, or if you just want to do it quickly, these are the four libraries you need to install: SQL Alchemy, LXML, HTML5lib, and then the beautiful Soup4 library. You can do this either with pip or conda. Alright, once you've installed these libraries and reference a notebook, you're ready to get started. Let's go ahead and jump to the Jupyter Notebook and show you how to read and write files with Pandas. Alright, here we are at the Jupyter Notebook. Keep in mind that as we reference the files, such as the example CSV file and the example Excel file, you'll need to make sure they're in the same location as your Jupyter Notebook is. In order to check the location of your Jupyter Notebook, you can just go in a cell and type pwd, do Shift-Enter, and it'll report back the location. This is the same file location the example CSV file and the example Excel file should be in. If you've downloaded the entire repository of notebooks and are working in the Data Input and Output section or notebook, you should be fine by just referencing the files as if they're already there. Okay, let's go ahead and show how to open and read CSV files. In order to do this, you can just say pd.read_CSV. And then begin typing out the name of your CSV file. In this case, I know it's called the example. So as I start typing this out, a nice trick is to click Tab, and it will autocomplete the file name. In your case, you may just have example, not example.csv. Let's go ahead and read that in. I did Shift-Enter, and now I can see the CSV file as a data frame with the columns A, B, C, and D, and 0, 1, 2, 3 as the rows. Note that if I want to read any files, I just use the read underscore command, and I can click Tab here, and I get this drop-down menu of the variety of formats that Pandas can read from. So Pandas can read from even your clipboard, CSV, Excel files, HDF files, JSON, pickles, SQL files, tables, etc. Just keep that in mind that you have a lot of options here. Right now, we're just going over the most common ones. Okay. In order to write to a CSV file, you're going to need a data frame. So I'm going to go ahead and just say df is equal to pd.read_CSV. And again, I'm just going to do example, tab autocomplete here. And now I have df as that same example df. So I've actually saved it to a variable. Off of a data frame, you can say to underscore. And if you click tab here, you'll notice now you have a variety of formats that you can write to. It's basically almost all the same formats that you could read from. So I'm going to go ahead and say df underscore to CSV. I'm going to label this my underscore output. And the other thing I'm going to do is say index equals false. And the reason for that is because I don't actually want to save this index as a column. Let me go ahead and show you what happens if I don't put index equal to false and I just put df to CSV. I'm going to go ahead and say pd.read underscore CSV, and I'm going to read the file I just saved, my output. Note, I get this column here called unnamed 0, and that was the old index. Now, if I say df to CSV and set index false and run that cell, and then if I read my output again, then I won't actually save that index and I will automatically assign a range index to the data frame. Keep that in mind as you're saving your CSV files, whether or not it's appropriate for you to say index equals false. Alright, now let's go ahead and move on to reading and writing from Excel files. Pandas can read and write Excel files, but you should keep in mind that Pandas can only import the data. It can't import formulas or images or things like macros. Using that with the read underscore Excel method may cause Pandas to crash. Another thing to note is that you may get an error asking you to install the XLRD library. That should have been automatically installed if you use the Anaconda distribution, but if you did not, you'll go ahead and go to your terminal, and in your terminal or command line, you'll type conda install XLRD, or you'll do the same thing with a pip install. Again, you're not going to do this in a cell, you'll actually do this at the command line or terminal. But hopefully if you did the Anaconda distribution, they should have automatically installed along with Pandas. Let's go ahead and see how this works. I'm going to go ahead and show you the Excel file I'll be working with. Here I have a very simple Excel sample. In fact, it looks almost the same as the .csv file we were working with, except here it's denoted that it's in sheet 1. And basically what Pandas thinks a workbook is that a workbook is just a bunch of sheets and each sheet is a data frame. Meaning I can say pd.read Excel. I pass in the Excel file name, the XLSX file. A good trick for this is to begin typing the file name, press tab, and select it. Again, this only works if the Excel file is in the same location as this notebook. If it's not, you'll need to pass in the whole file path. And then you can say sheet name, and then pass in sheet 1. We'll go ahead and read this, and we get the output we expected. And that's basically it for reading from an Excel file. You pass in the file, and then you pass in the sheet name you want, and Pandas tries its best to read it in as a data frame. Writing a data frame to an Excel output is also a very simple process. You just take the data frame you want to write to Excel, say to underscore Excel, pass in the name of the Excel file you want to save it to. Let's go ahead and make a new one called Excel sample2.xlsx, and then we can also specify a sheet name if you want to. Something to note is that when you're saying to underscore Excel, for whatever reason, Pandas, you need to write in sheet underscore name and then the name of the sheet. We'll go ahead and put in new sheet. All right, let's go ahead and run this. And that's it. We've saved it to an Excel file. Now let's go ahead and move along to working with HTML. Again, you'll need to install quite a few libraries in order for this to work, and you'll probably need to restart the Jupyter Notebook after that. You can go ahead and check out the notes for this lecture, the notebook for it, to get a list of all the libraries you need to install. I'll go ahead and go to the beginning of this lecture where we showed the list of libraries. Let's talk about HTML input. Here, I have a link to the FDIC.gov failed bank list page. And here's just a list of all the failed banks by the FDIC as far as them keeping track. It's the Federal Deposit Insurance Corporation. And here we have a bunch of failed banks, the closing date, updated date, etc. But this is basically just an HTML link. This link is in the notebook, so you can go ahead and copy and paste it from there. I'm going to go ahead and copy this link and try to read it in with Pandas. In order to do this, all I have to do is say PD. Well, let's go ahead and say data equals PD dot read HTML. And then as a string, I'm going to pass in that actual HTML link. It'll take a little bit of time to read it, but it should work out if you have all the libraries. Okay, looks like it worked out. Something to note here is that usually this isn't going to directly relate to a data frame. If I check out what data is, if I say type, you'll notice that it's actually a list. And essentially what Pandas tried to do was to find every table element that was in this HTML file. And if you're familiar with HTML, you know that if you can right-click here and view page source, you'll have this list of actual HTML code. And if you're familiar with HTML, you'll know that you can actually look for, just like there's list classes here, there's actually table references. So there's table markings in here in the HTML code. And that's basically what Pandas is going to do. And it's going to make a list of them and convert each item in that list into a data frame. And what you're going to do is just cycle through that list until you find what you wanted to look for. In this case, it should be the very first item in the list. So if we say data at point 0, so the very first item in that list, that's the data frame we were looking for. Bank name, city, updated date, etc. Let's go ahead and just check out the head of that data frame. And that's what this looks like. Again, some things don't copy over exactly. You get a bunch of null values, but keep in mind, Pandas is basically just reading this HTML file as best as it can. Alright, that's HTML, which is essentially just web scraping of Pandas. Let's finally move along to our last topic, which is working with SQL. Now there's quite a few notes in your notebook regarding SQL and Pandas. Pandas isn't actually probably the best way to read a SQL database because there are many flavors of SQL engines, such as PostgreSQL, MySQL, SQLite, etc. What we're going to do here is just actually build a very simple SQL engine that's going to be just temporarily held in memory in order to show you how you can use Pandas to read tables completely as data frames. However, I would recommend that you actually do a search for a specific driver dependent on your specific SQL engine. For example, if you go to the notebook for this lecture, you'll see that if you're using PostgreSQL, you should actually use a library called PsychoPG2, which is specifically designed to work with PostgreSQL. Or if you're using MySQL, you should use PyMySQL, another library specifically designed for that specific flavor of SQL. Right now, we're just going to do a very simple example of how Pandas could read in an entire table in SQL if it had to. What you'd end up doing is saying from SQL Alchemy imports create engine. And this is going to just allow us to create a very simple SQL engine in memory. I'm going to go ahead and say engine is equal to create underscore engine. And here I'm just going to type in SQLite 3// and then memory colon. So I have SQLite colon 3// colon memory colon. I'm going to go ahead and run that. And this little thing, this little line of code has created a very temporary, very small SQLite engine database that's running in memory. I'm going to go ahead and take my data frame, that df, and I'm going to say to underscore SQL, and I'm going to write it to that very temporary engine that we have running in memory. So what you're going to do is you're going to say to SQL, you're going to pass in what you want this table to be called. So we'll go ahead and call this my table. And then you pass in the SQL engine you're working with. In this case, it's just an engine. Now, this engine is going to be a connection usually. I would recommend you read through this documentation thoroughly. But again, like I mentioned earlier, Pandas just by itself probably isn't the best source for you to actually read SQL into Pandas directly. You should probably look for specialized Python libraries for whatever version of SQL you're working with. But as far as a very simple setting, you can just say df to SQL, pass in the new table name you want, and then the connection to your SQL engine. And now I'm going to go ahead and say SQL df and actually read back that table. So I'm going to say pd read underscore SQL. I pass in the name of my table. In this case, it's my table. and then I specify the actual connection I want. So CON, and that's just the engine, that very small SQLite database that's happening in memory. And if I go ahead and read that and check out what that looks like, I get SQLDF, and notice that the index is a new column here. All right, go ahead and feel free to post to the Q&A forums if you're having trouble finding a particular library that works with your SQL engine or your flavor of SQL. As far as this lecture, the main thing to get out of it is how to read and write to CSV files, because we're only going to be working with CSV files for the rest of the course. As far as your own personal usage, hopefully you can just check out the read underscore methods. There are a lot of them, and you can just look at the documentation or reference a notebook for how to actually read to a Pandas data frame. All right. Thanks, everyone. Hello, everyone, and welcome to the operations lecture. In this lecture, we're just going to review some of the most important operations for Pandas, as well as learn some useful operations that we haven't gone over yet. Let's go ahead and jump to the Jupyter Notebook to get started. All right, here I am at the Jupyter Notebook. I went ahead and just copied the first cell of the operations notebook that goes with this lecture in order to create this data frame. It just has 3 columns, call 1, call 2, and call 3, and it has an index of just numbers, 0, 1, 2, 3. In call 1, we have 4 digits. In call 2, we have 4 numbers here, but notice that 444 is repeated. And then in call 3, we just have 4 sets of strings. Let's talk about finding unique values in a data frame. There's 3 main useful methods concerned with finding unique values in a data frame. Imagine we wanted to find all the unique values in column 2. The method we can use for that is just the unique method. And this will return a NumPy array of all the unique values in column 2. Instead of actually wanting the array of unique values, let's say you just actually want the number of values itself. Well, there's 2 methods for this. You could just check the length of the array that gets returned, and this would respond to 3. There's 3 unique values in column 2. But Pandas actually has a built-in method for this, and it's just nUnique. And if I run this cell, I get the same answer. All right. So we have unique for actual returning an array of unique values, and nUnique if I want the number of unique values. The last useful function I want to show you is value counts. And this basically means if you want a table of the unique values and how many times they show up. You can just use value underscore counts as a method, run this, and this returns how many times each unique value occurred in that column. In this case, 444 occurred twice, and the other numbers occurred 1 time each. All right, those are 3 very useful methods, and you'll find yourself using them often in the exercises. Let's go ahead and talk about selecting data. We've already gone over conditional selection, but I want to reemphasize just how important it is and how powerful it is as a tool. We have our data frame, df, and we can use conditional selection by passing in a conditional selection statement, such as saying, return the df where column 1 is greater than 2. And this will return all the rows of the data frame where column 1 happened to be greater than 2. And remember that this command inside is essentially just a Boolean series of false, false, true, true. Now, as a quick reminder, if you want to combine conditions, you can wrap these conditions in parentheses and then use either an ampersand or a pipe operator, depending if you want and or. And then you can say another condition, such as where call 2, let me pass this in as a string, has equality with 444. And this should return just that last row, 3. And there it is. Okay. That's just a quick reminder of how to select data using conditional selection. Now let's talk about the apply method. The apply method is going to be one of the most powerful tools in your tool belt when using Pandas. So let's go ahead and show you how it works. Imagine we have a function, def times 2, that takes in a value x and then returns, let's say, x times 2. All right, a very simple function. Now, you know that you can already grab, for instance, a column and call a built-in function off of it, such as the sum. And that will return the sum of the column. But what if you wanted to apply your own custom function, such as times 2? Well, Pandas has the ability to do that. you can just say the column name and then dot apply, and then you just pass in whatever function you want to apply. In this case, we're going to go ahead and apply times 2. And this will broadcast that function to each element in that column. 2, 4, 6, 8. You can also apply built-in functions, such as length. For instance, if we take a look at column 3, we had a bunch of strings. Let's say we wanted a column that represented the length of each string. Well, then we could just say apply and pass in len. And that returns the length of each string, which in this case was 3 for all of those strings. Apply is going to be especially powerful when you combine it with lambda expressions. That way, you don't need to take the whole time to define an entire function if you're just going to apply it once. For instance, let's go ahead and make a lambda expression out of times 2. I'm going to go ahead and say lambda x colon and then just x times 2. And I'm going to apply this to column 2. Let's go ahead and see how this works. And there you have it. We were able to multiply each value in that column by 2. And we were able to do this without having to write an entire function for it. We just did this as a lambda expression. And this is the sort of thing you're going to be using all the time as you get more and more comfortable with Pandas. This is probably one of the most powerful features of Pandas, the ability to apply your own custom lambda expressions or functions. Alright, let's talk about removing columns. Again, if we have df, we want to, let's say, remove column 1. We can just say df drop, pass in the column we want to drop, col1, and then remember, since it's on the columns, we have to specify access is equal to 1. And this will drop that column. If we want this to occur in place, we have to specify in place equals true. Let's go ahead and not run that so we retain our original data frame. If you want to get the column and index names off a data frame, those are actually just attributes of the data frame itself. Meaning you can say df columns, and it'll return this kind of index object, which is essentially just a list of column names. This is going to be especially useful when you're trying to index a column and maybe the spacing is weird or you can't quite figure out what the string is. You can just call df.columns or whatever your data frame name is, and it'll return this list of column names. And you can actually do the same thing for an index. You can say df.index and it'll give you information of the index. In this case, since it's a range index, it actually just reports back the start, stop, and step size of the index. Alright, let's talk about sorting and ordering a data frame. Here we have df, and imagine we wanted to sort it by column 2. Essentially, we want 444 and then 444 again before we see 555 and 66. We can use sort values in order to do this. You call df sort underscore values, and then as an argument, you say by. And we check shift tab here, you can say by, and you could order this off of either the rows or the columns. But essentially, you just pass in as an argument the column you want to sort by. So I want to sort this by column 2, and you can say just column 2 as such, shift enter, and now I've sorted this data frame by column 2. Note how the index stays attached to the row, so you don't ever lose that information there. And that's the same thing as just saying by column 2. It's the same thing, it's because it expects by to be the first argument. Alright, let's talk about just a couple more useful operations. A really useful method to find null values in your data frame is the df is null. And this will return a data frame of booleans indicating whether or not the value was null or not. In this case, we get a boolean of all falses because we have no nulls in our data frame. Thanks everyone, and I'll see you at the next lecture. Welcome back everyone to this last technical topic lecture on pivot tables with Pandas. So let's talk about pivot tables. They allow you to reorganize data, and they allow you to refactor cells based on columns and a new index. And this is actually best shown and explained visually. So let's take a look at this visualization from the Pandas documentation. Essentially, the main idea is that a data frame with repeated values inside of its columns can be pivoted for reorganization and for clarity. So here we have an original data frame on the left-hand side, and we have 4 columns, foo, bar, baz, and zoo. And then we're going to call the .pivot method on this data frame, and we have to choose what the new index is, what the new columns are, and then also what the new values are going to be. So we choose columns from the original data frame. So essentially we have 4 choices from the original data frame: foo, bar, baz, and zoo. And then we pass in those columns to define what sets we want for the new index, columns, and values. And you should notice that how the choices for the new index and the new column values should have repeated values in the original data frame. So in the .pivot command, we chose the foo column for the index. And you'll notice the foo column in the original data frame has repeated values. We have 3 1s and 3 2s. So then when it moves on to the index, we essentially just take the unique values there. And then we also can see that the bar column is what we pass in to now define the columns after the pivot. So then we can see that we have the repeated values ABC, ABC. And now each of those unique values is a new column. And then we have to decide where are we actually going to match up for the cell values. And we decided to choose the baz column for that. We could have also chosen the zoo column as well, since those are all unique values. Usually your values should be more or less unique, but what this is actually showing you here, as far as the pivot is concerned, is it's just showing you what values are related for each unique value matchup in the index and column choice. So if we take a look at the original data frame, for instance, what lined up with foo is equal to 2 and bar is equal to A? That question is a little harder to answer in the original data frame because I have to first go to the foo column, look at the number 2, then I have to look at the bar column and see where that matches up with the letter A, and then finally I can see, okay, baz was number 4 for 2A. If you have that sort of question, it'd be easier to just do a pivot table here, or really it's called a pivot method, and then this is a lot easier to answer of what value for baz is matching up with foo of 1 and bar of A. We can just quickly see that it's something like 1. Okay. So you should also notice how all the information from the zoo column is actually now discarded. So it doesn't actually come over after you call .pivot. And probably the last but really important note here, while we're calling the .pivot method, not the .pivot table method, which we'll discuss in just a little bit, but when we're showing the .pivot method, we're not actually displaying any new information. It's just merely being reorganized. In fact, slightly less information is being shown after the .pivot command because we dropped the zoo column. But let's explore now in a Jupyter Notebook both the .pivot method and the pivot table methods in Pandas. All right, here I am at the Jupyter Notebook. Let's go ahead and read in the file we're going to be working with. It's located underneath the Pandas folder. You simply say pd read CSV, and then we're going to call sales funnel CRM.csv. So CRMs are customer relationship management systems. It's really common that people use pivot tables on these. So we're going to go ahead and explore it just a little bit. Here we can see, let me zoom out a tiny bit so we can get a scale of what's happening here. We have an account number. We have a company that we're trying to sell something to. We have a contact at that company. And then the person on our team, who's the account manager for that particular contact, the product we're trying to sell to them, the number of licenses we're trying to sell, the total sale price, and then the status, whether we've already presented the opportunity to them, whether it's under review, whether we lost it, or if we've already won and closed the deal. Okay, so very typical to see a CRM sales funnel data frame like this. So let's go ahead and explore how we can use the pivot method to try to get a little more clarity if we're trying to answer some questions. And I would encourage you to take a look at just the help documentation for pd.pivot. By calling help on it, you'll actually see you can create this little data frame, the same one I showed in the previous slides, and then it'll show you a bunch of commands you can actually call in it. So super useful. Go ahead and check that out. But we'll go ahead and explore it on our own right now. So we have this data frame. What we're going to do is let's imagine that we wanted to know how many licenses of each product type did Google purchase. So if we come over here, we can see I have the company. I could see Google, and then I have the licenses, but I want to know how many licenses of each product type did Google purchase. And right now, the way it's set up, it's a little hard to answer because I have these other columns in the way, so I have to go from company Google and then jump over. And the other thing, if this was a really large data frame, I wouldn't actually know if Google was further down the data frame because maybe Google would have been in row 100 and I wouldn't have been able to view it. So luckily right now, it's the first 3 rows, but that's basically just for the purposes of this presentation. So what we want to do is we want to know how many licenses of each product type did Google purchase. And currently it's a little hard to read this way. So let's go ahead and pivot to reformat. And the first step you should do is just select the 3 or a few columns you want to actually work with. And so what I want to know is the company, specifically Google, the number of licenses, and the product for each one. So we're going to come over here and just take a subset. We're going to call it licenses is equal to DF, and then pass in that list of columns. I'm going to work with the company column, the product column, and then licenses. And I just want to note here, you don't technically need to do a pivot to answer this question, but it is going to make it a lot easier, especially if the data frame could not all be read at once. So then we take a look at these licenses, and now I only have those columns, so it's time to pivot. So what we're going to do is call pd.pivot. The data that we're going to pass in is licenses, and then I'm going to set the index to be company. Recall that typically you want your index column that you're providing to have repeated values, because really what's going to happen is the index is just going to be the unique then company. So we'll have an index or labeled index for Google. And then that means I want the columns to be the various products that we sell. So here we're going to have analytics, prediction, tracking, and keep in mind if there's products that we haven't sold licenses to Google yet, they'll just show up as NA when it comes to the actual license number. And so the value I want here is going to be, or the values I should say, it's going to be the actual licenses column. Okay, so let's go ahead and pivot that. And you'll notice after running this, you have a bunch of not a number or null values. And that makes sense because we haven't sold every single product to every single company. And in fact, if we take a look now at Google, and you could always just use indexing to grab only Google off this data frame that's returned here, is that we can see we sold 150 licenses for analytics, none for GPS positioning products, and then 150 for prediction and 300 for tracking. So now it's a lot easier to answer the sort of questions of how many licenses of each product did we sell to a particular company versus trying to come back here and then use filtering to do that. Granted, you could do this and answer the questions without a pivot table. You would just start saying, okay, give me the DF where the company is equal to Google, and then you would start looking at the product and licenses company that way. But here is a really nice presentation where you can then start comparing, and maybe you can answer a question like, what was the company we sold GPS positioning to? And very clearly you can see it looks like Cisco was the only one we actually sold something to, in regards to GPS positioning. Okay. So that's just the pivot command. Recall pd.pivot. Remember, it's pd.pivot, not df.pivot. You call it off of Pandas. That just reorganizes your data based off a new index, new column values, and then what you actually want the cell values to be. What we want to do a lot of times is actually then perform some sort of aggregation call on top of this. And that's where the pivot table or pivot underscore table comes into play. So the way this works is if we take a look at our original data frame, we have this information, and let's imagine that we wanted to now get maybe the total sum of the licenses and the sum of the sale price for each company. Essentially trying to answer the question, how much have I actually sold to each company, total sum. Technically, you could do this with a group by, but it's possible with a pivot table. Depends on exactly what you're trying to achieve, which method you choose. I personally prefer group by method calls, so I try to do that before I start using pivot table. But again, it's kind of up to you. So we're going to pass in our data frame first into pivot table, and then we have to choose what's the new index going to be, which is essentially what you're actually going to group by. So we say, okay, go ahead and set the new index to be by the company. So it's going to essentially group by the company column. And then we're going to pass in the data frame as our data source. And finally, what's the aggregation function you want to actually use? You can use any of the aggregation functions we've discussed earlier in the group by methods. You just pass it in as a string. So in this case, I'm going to sum them up because the question I'm trying to answer is how much have I actually sold per company? Now keep in mind this will actually perform a sum for every single numeric column. So if you run this, it actually also sums up the account numbers for every single company here, which doesn't really make sense to sum up all the account numbers for Google. So that's kind of meaningless. but it does make sense to sum up total licenses sold and the total sale price. So here I can see now quite easily that I have sold 600 licenses to Google for a total number of sale price of like $3.15 million. Okay. So again, keep in mind, we could technically be answering these questions with a group by. I could have just said DF, group by the company column, and then call sum on this, and that gets you the same results. So whichever one you prefer. Again, I mentioned that I'm partial to preferring group by method calls. I think they're a little simpler and easier to read, but if you're coming from Excel and deal a lot with CRM data, you may prefer the pivot table methods. Now, I mentioned earlier, it didn't really make sense that the account number here is also summed. So what you can do is if you want, you can actually provide the values argument and provide a list of the columns that you're actually interested in, essentially selecting them after the fact of the pivot table. So then we can say sale price and licenses are the values I'm actually interested in seeing the sum for the company. So you can see a pivot table is kind of pretty readable. You can just say, okay, here's my data source. I want the index to be grouped by company. Give me the sum of licenses and sale price per company. So you can see here, after you run that, you get licenses and sale price instead of also the account number. And now finally, let's go ahead and go through one last example. It's going to be analogous to the multi-level index examples we saw when we group by multiple columns. What we'll do here is we'll go ahead and say use pivot table, but I'm going to pass in 2 columns for the index. So if we take a look at our original data frame, DF, I have both a contact and an account manager. And we can see that account managers can have multiple contacts. So here we have Ed Thorpe with a contact of Larry Pager at Google, but then also Elon Musk at IKEA and Tesla. So let's imagine I wanted to just see the account manager and then maybe the total number of licenses or the total number of sales that person has come into play with, as well as the list of their contacts. So essentially what I want to do is I want to group by the account manager and then the contact and get the total sale price per contact. So let's go ahead and try that out. We're going to say PD dot pivot table. I'm going to pass in DF since that's what I'm working with. And then for the index, I want my outside index to be that account manager. And then I want the inside level index to be their contact there. The actual values I'm interested in, let's go ahead and just say I'm interested in the sale price. So we'll say sale price. And then I have to choose an aggregation function. So we'll say, give me the sum of the sale price. So what this is going to answer is the total sum of the sales that an account manager has done per contact. So we'll say then aggregation function is equal to sum. So we run that. And here we can see we have 2 account managers, Claude Shen and Edward Thorpe, and then their various contacts. There may be people with 0 contacts or 1 contact, 3 contacts, etc. This number doesn't have to be fixed. And then the total sum per contact. So it's essentially kind of a group by account manager, then contact, and then sum, and only call the sale price column. So keep in mind, the columns are optional. They provide an additional way to segment the actual values you care about. And the aggregation functions are applied to the values that you list. So what we could do is say here, add in a parameter called columns. And we're going to add in a parameter there for product. Go ahead and say product there, run that. And so now what this is going to show you is the sale price separated out by product. So here we're dealing with kind of 2 tiers of multi-index levels. 2 tiers for the index and then 2 tiers for the actual columns where we have an overall sale price, but now it's broken down by the actual product type. So we've sold, for example, Ed Thorpe has sold Elon Musk 7.35 million total in analytics and nothing in GPS, 700,000 in prediction and nothing in tracking. Now, we don't actually know if Ed Thorpe has done all these sales in one go for Elon because right now we're just taking the total sum. So just keep that in mind. And something to note here is if you don't want these to be null values, maybe it makes more sense to fill these in with 0. There actually is a default fill value parameter, very similar to the fill values we saw when we were talking about dealing with missing data. You just say fill underscore value is equal to 0, and any null values we fill with whatever value you want. So in this case, we'll just go ahead and put them at 0 since that makes sense for us. And another thing I want to point out is you can technically pass in more than just a single function call here. You can actually pass in direct NumPy calls. So if you want, you can pass in a list here. Instead of the string sum, I could say np.sum, and that will run the NumPy sum function. So you get the same results here. But what's nice about doing this is I can actually then call for multiple NumPy functions like np.mean. So then I want both the total sum. So notice here we have yet another outside index level sum of the sale price per product. And then we can also get the average. So run that as well. And you start getting these very large data frames here. So then we can see the total sum that Claude Shannon has sold in Analytics to Cindy Phoner. And then I can also get, on average, what is the sale price? Are they doing this all in one go, or are they doing it in 2 goes, etc.? So you'll notice that we can see here directly the mean of Analytics sales versus the total sum of Analytics sales for Claude Shannon's contact Cindy Phoner. And something to keep in mind, especially with the pivot table command, is that it can get really messy really fast and really hard to read really fast because now you're just aggregating too much data. So always keep in mind, you're trying to simplify things, not make them more complicated. So for example, in this case, I set the products to the columns, but it might even make more sense to just do sum or mean just one at a time. So just have np.sum here as a single data frame. And this is still maybe not as easy to read as setting the product as another index. So maybe we, instead of just having it as a column, we remove that there and then have it as yet a third index. So we can say product, run that, and then I get this nice little table. So whether or not this is easier to read really depends on, again, who you are, what you're trying to answer here. But remember, you can always kind of play around with having something in an index versus spreading it out to a column. The very last thing I want to point out here is there's a convenience parameter called margins, and it's a little not clear from documentation what it's actually doing. But essentially what it does is it's either true or false. It's a bland default is false, but what you can do is set it to true. And what it's going to do is give you a grand total at the very end at the margin. So if we take a look at that, what it's going to do is if we exit out and just say here at the end, comma, margins is equal to true, and run that, you'll notice at the very bottom, it does this kind of grand total. So kind of useful for certain situations, especially for things like formatting. So then you could save this, save it as an Excel file, send it to your manager, and then she or he will be very impressed by all the work you did in just one line of Pandas. Again, kind of a really long line, so always keep in mind what questions you're trying to answer and whether or not it's worth it is trying to figure out the pivot table. Thanks, and I'll see you at the next lecture.